Hello. Okay, so I mean, good afternoon. So our next session chair is Professor R.K. Singh. He is going to chair this session.
Hello, welcome to session after lunch. I think all of you enjoyed your lunch. I thought you will enjoy very much. Variety of stuff was there. So in this session we have three talks, and first talk is by Satyan Kumar. That is 1 hour talk, and it's a pleasure and privilege to introduce Professor Prem Kumar. He is a professor of information technology at McCormick School of Engineering and Applied Sciences at Northwestern University. And his research focuses on quantum photonic devices, applications to sensing, imaging, communication, other areas. And he's fellow of all the academies, AAAS, IEEE, APS, OSA, Optica now. So he's IOP UK. So he's fellow of all over the world. And he has guided more than 55, now more than 40 students. Very soon he'll be providing completing PhD in the supervision, and more than 500 papers. His students are in academic industry, national lab everywhere. So, and in he has got many awards that includes the Research Excellence Award from Provost Office at Northeastern and distinguished lecturer for the IEEE Botanic Society. Herman, Herman Haas lecturer at MIT, and there are many more. So I think enough of introduction.
Thank you, RP. Yes. All right. Trying to figure out where I should stand. Here's better. All right. Good afternoon. Well, first of all, thank you for the kind introduction. Thank you for the invitation. And what I thought I will tell you a little bit about what excites me in quantum networks by painting a big picture. And that big picture starts with classical networks and how we got here. I think that's a very illustrative for understanding what quantum networking needs to be, what it is, and how do we engineer it. So with that, let me tell you a little bit about what often people would call bit revolution. We're all experiencing it today. You all have your handheld devices. You can basically telepresence yourself, and we are telepresenting this slide set. So this all started back in the 1950s with the invention of the transistor, late 50s, and really took off in the late 1950s when integrated circuit came on the scene, and companies like Intel were formed, and they started to produce small-scale microprocessors for computing. And at the time, people like Vint Cerf, Bob Kahn, these are what they are called internet evangelists today. They started to ask the question, what would happen if we were to interconnect a few of these devices together? And of course, what they had in mind was, could we, by interconnecting small scales classical computers, they could do more than what the computers could do themselves, for example, file sharing, message sending, and so forth. One of the examples being email. Today, every two-year-old takes email for granted, right? And if you go back and look at the history, this churn that occurred between development of the computing devices all the way up to the interconnectivity, starting with the ARPANET and then NSFNet, invention of the TCP/IP protocol. TCP/IP stands for Transmission Control Protocol Internet Protocol, which is what drives the connectivity between the various devices. And this churn, these protocols, the architectures, setting up test beds for classical networks, told us what kind of devices are needed. Because at the time when they first started to do networking, they didn't really have all the devices. And by creating an architecture, by setting up test beds, this churn taught us what devices are more important, what should we do first, and then scale the network accordingly. Today, we are in the age of big data, AI, distributed computing, cloud computing. In fact, all the ride share applications, mapping applications, everything is a result of that. So the main message here is that this bit revolution built upon advances in computing. I only mentioned beginning of the computing, but of course, along the way, we went through distributed computing and now cloud computing, and all the advances come together with interconnectivity between them. That interconnectivity initially was powered by just classical electrical communications, and optical communications came along, and then wireless communications for the edge nodes. So the question that we have to start asking now is, would there be a similar qubit revolution? And that's an important question to ask, because similar things are happening in the quantum computing space. Early work on QKD networks, and this talk is not going to be focused on QKD networks, but you heard a couple of talks earlier today focusing on QKD. But in the early 2000s, enough work had gone on such that people were beginning to demonstrate these so-called NISQ-era computers, noisy intermediate scale quantum computing hardware. And of course, in the last 3-4 years, you've been hearing about computing advancing by leaps and bounds. Just recently, you've heard about logical qubits, true quantum computation on in a fault-tolerant way, at least the beginning of those. And the question then we have to ask is, what would happen if we interconnect those quantum computing hardware by communicating devices, systems, and so forth? And in this case, it'll have to be quantum communication, communicating systems. And of course, the other impetus to all of this is that the quantum computing companies, I have not tracked the advances here. I made this slide back about 5 years ago. Uh, as I said, a lot has happened in this space, but almost every quantum computing hardware company is recognizing that scaling quantum computing hardware to a level where it can do meaningful quantum advantage. That is, it can solve problems that classical computers cannot. That these computing devices have to be modular because scaling is challenging, not just because to create the larger and larger number of qubits on a particular substrate, whether that's superconducting substrate or whether it's an ion trap based system or a photonic system. Your integrated photonics or integrated platforms are not big enough. Wiring is a problem. So every quantum computing company's roadmap today involves interconnectivity, modularization, and that necessarily entails communicating between those separate modules. So with that, we have to ask the question, how do we interconnect quantum computing hardware or quantum memory devices, access points, and so forth? Very similar to the kind of things that have been done in scaling up classical communications and computing to the point of ubiquitous availability. So with that, I want to step back and for the sake of the students, I want to introduce what we really mean by quantum communication. And then in order to build to that, let's just step back even further and ask, what do we mean by communications in the classical sense? And at a very high level, communications involves a device. In this case, it's probably your smartphone. It has a communications buffer, and these red dots are classical bits that are stored in that buffer, and you want to communicate some information stored in those bits. And let's say the device is in the possession of Alice, a typical sender, but these bits are 0 or 1. And on the right side, there's another user, Bob, has a similar device that has bits, that stores bits, and then eventually connect to the memory and interface to the person who's trying to communicate. In the 1940s and 50s, Claude Shannon taught us that irrespective of the channel that connects Alice and Bob's devices, it is always possible to do error-free communication below a certain channel capacity. That channel can be free space channel, that channel can be a fiber channel, no matter what its characteristics. So long as you are below the channel capacity, you can do error-free communication. Of course, it took a long time to develop efficient codes to do error-free communication in a very, very efficient way. Today, for example, it's common to have 20%, 25% overhead in error correcting systems, and you can have signal to noise ratios that are like 10 to the minus 3, and yet you can do error-free communication because of these error correction things. So naively, one can ask, can we do something similar? Before I go there, so this is today, almost everything we do, as I mentioned before, is really a highly interconnected computing/communications infrastructure. Today's supercomputer, this is Summit, this is from a few years ago, is basically a highly networked, millions of CPUs connected together, these days CPUs and GPUs connected together with high-speed communications. It used to be electrical communications, now it's all fiber optics. A data center is also very similar. I think I lost the battery in this now. So a data center is also a similar network, and the whole globe is kind of engulfed in fibers, lots of fibers all the way around. And for the last mile, we have these metallic trees that you walk around that you see. These are the wireless transceivers that you interface with. So we asked the question, can something similar can be done or would happen for quantum communications and quantum computing infrastructure? Of course, now Alice has a device, potentially a quantum computer or a quantum memory element or something in her possession. And these red dots here are not just bits that are in 0 and 1 states, but they are quantum bits or qubits that can be in 0 and 1 states and any superposition thereof. They could be photonic qubits, they could be polarization of the photon, it could be path entanglement, a photon in one path or the other path, or they could be electron spins or any modality with 2 states. Then that quantum state psi, often we represent that as a Schrödinger cat state, just that it's a superposition of a alive and dead cat, pictorially speaking. And similarly, Bob has a quantum register in his possession, and we asked the similar question, can one do communication below a certain error channel capacity or something like that? And immediately you realize that kind of line of reasoning does not work, because if Bob had the same quantum state in his possession that Alice had, that's equivalent to copying a quantum state. And we know from the fundamental no-cloning theorem that an unknown quantum state cannot be copied. And unknown quantum states are the more interesting one, because remember, the goal is to interconnect quantum computing devices. So the states that are taking part in some computation, they're not known. You can't really measure them. So you have to let them intercommunicate between devices. And of course, this thing came back. This measurement and recreate possibility doesn't work either, because you can't really measure an unknown quantum state. And so, because Heisenberg uncertainty principle comes in the way. So it seemed like something akin to classical communications and networking was a no-go until the teleportation protocol was invented by Bennett and co-workers in 1993. What they showed was that you need a new resource. If Alice and Bob can pre-share a pair of entangled qubits, let's call that an E-bit, an entangled pair of qubits. If they, in this case, written as T stands for transmitter, R for receiver, but it's a singlet state, 0 and 1, let's say. If Alice and Bob can pre-share entanglement and they have an ability to store it, then Alice can actually send her qubit, something she has in her possession, by making a joint measurement on that qubit and half of the entangled bit in her possession. That's a joint measurement, kind of a Bell state measurement, so to speak. That 2-qubit joint measurement has 4 possible outcomes. That's 2 bits of classical information. If that classical information is classically communicated from Alice to Bob, then Bob can use that information to manipulate his half of the entangled bit. Turns out that's the result in this paper. That transformation, that conditional transformation upon learning the results of that 2-qubit measurement, gives him exactly the state that Alice had. And this protocol has been known as the teleportation protocol. It does not require a quantum channel at the time of quantum communication, provided Alice and Bob has this new resource of entanglement. So you consume entanglement while you communicate. And in the process, you obviate those conflicts with quantum mechanics, because in the process of joint measurement, Alice's qubit is actually destroyed as it appears in Bob's possession. Okay? So this realization of the teleportation protocol allowed people to start thinking about creating networks which can interconnect quantum computing or quantum sensing or any of the quantum hardware. Of course, this is very challenging. And this talk is about engineering challenges. And from here on, I'm going to talk a little bit about what those challenges are, how to overcome them, what we have been doing, and where we need to go. Okay. So there are lots of challenges. First of all, if Alice and Bob are going to pre-share entanglement before doing any kind of quantum communication, there has to be a way to generate, that is, you need ubiquitous availability of entangled photon pairs. And I'm assuming photons would be the entangled particles because we want to go distances that are longer than perhaps a micron or a millimeter, where possibly electronic or any matter modality of entanglement could be moved from one place to another. We need technologies for storing those photons in long-term quantum memories, not only store them, but also recall them when you need to do the quantum communication. And then depending on that storage mechanism, you perhaps also need transduction devices so that the quantum state can be seamlessly moved from one modality, from a matter qubit to a photonic qubit, or from any one modality to another. And then we also need technologies for very efficient Bell state measurement, those joint measurements on 2-qubit states. And there, since we're talking about photonic systems, that joint measurement means the photon counting in some special way. If you just simply use a beam splitter to do 2-mode measurement, like the ones I will show you, you don't get all 4 Bell states. Most of the experiments that are done with photonic systems, they end up measuring only 2 of the Bell states. And of course, if you want to scale the network, we also need to pay attention to the losses in the fibers or free space channels, because loss is the bane of everything quantum. And if you lose those entangled particles as they are moving from one place to another, your rate of entanglement is going to be low, even though your teleportation may succeed, but the rate will be very limited because of the losses involved. So these are very hard challenges to overcome, but nevertheless, progress is being made. And none of these things really are fundamental challenges. Mostly they are engineering challenges. And of course, if you engineer things, sometimes those engineering challenges turn out to be of fundamental nature, and one needs to rethink how to engineer things in a different way. So okay. So as I mentioned before, most of the quantum computing companies are realizing that in order to scale, their computers need to be modular. And that's not a new story either, right? In classical systems, I've been buying personal computers for so many years. Every year or so, you buy a new computer for the same amount of money, you get twice the hardware. Faster, particularly in the context of hard disk drive, it's always the case. So you end up buying the same amount of hard disk, for the same money, you get twice the storage, basically. So same thing will happen. People will build quantum devices, and they will find that there's a sweet spot, a certain number of qubits, a certain processing speed, or certain quality of the entanglement, or 2-qubit gate fidelities, or quantum volume, or whichever way you want to quantify the progress in the computing devices. But then you will make many of those. It turns out to be cheaper to replicate, that is, make many of those and then try to interconnect. So the question then we have to ask is it possible then to take m of those n-qubit systems and interconnect them via quantum communication so that you can bridge this gap, that is the Hilbert space accessible to any distributed quantum protocol can access not just m times 2 to the n, which would be if you interconnect all those devices with classical communications. But if you interconnect them with quantum communications, the Hilbert space is 2 to the mn. For any reasonable m and n, that gap is pretty large. And if you can fill that gap somehow by perhaps distributing your n qubits between a communication buffer and a processing buffer, perhaps there is a way to scale quantum computing hardware. So this is sort of the motivation from a very high level, and to me, this is the only motivation that makes sense to develop quantum communications and networking, is to bridge this gap, because scaling quantum machines is daunting, no matter which type of machine you have or which type of substrate you use. Okay, so sorry, this is going the wrong way. And along the way in the networking, of course, I showed you before that diagram that I had started out with QKD networks. That line of research kept on going. And I have these couple of slides to make a very particular point. Of course, everybody knows of this experiment, and that's more or less probably is the reason for the National Quantum Mission here. And it's not only here, but also in the US, the National Quantum Initiative that we have. And I know firsthand because, as many of you know, I took a leave from my university, and I was at DARPA as a program manager. And I saw this front and center, the impact of these experiments that were done. This Messier satellite that China launched led to these experiments of entanglement distribution from space to ground to be able to do quantum key distribution or entanglement distribution over distances that just are not possible. 1,000 kilometers, there's no photon will, with any likely probability, will get through. And this satellite had a piece of hardware. This piece of hardware is a Sagnac loop polarization entangled photon pair source. That source was invented by us. It was invented. I had a system like this, although for CV, squeeze state generation, but Franco Wang in a joint project published exactly this source in his Reve paper in 2006. The Chinese saw the opportunity and they engineered it well, that it went up the rocket and very quickly was producing results that were very shocking to the world. Okay, so this was all engineering. Not only that, people in Singapore followed it up. This is again a PhD thesis of Z Tang in 2018. They wanted to do quantum key distribution on a CubeSat, using a CubeSat. And they designed a photon, in this case, it's not an entanglement source, but it's just simply a photon pair source. But during the launch, a mishap occurred that their rocket blew up. They launched on this launch service provider, and their rocket blew up. And they recovered from the rocket wreckage their device. And lo and behold, this thing was so well engineered that even after the explosion, there was hardly any degradation in its properties of photon pair generation. So the point I want to make here is that these kind of devices can be engineered, they can be robust, and they can be put out into the field, into a space environment to do interesting things. And QKD has been, of course, the front runner in all of this. Many quantum networks have been built, and I'll show another one in a moment later. But at the same time, that experiment by the Chinese, launch of the satellite and doing the experiments, as I said, ruffled a lot of feathers. And in the US, workshops were held, how do we create a foundation for quantum industry in the US? This is from 2017, and Jake Taylor, who served in the White House Office of Science and Technology Policy, organized a workshop. And at the time, I had just come back from DARPA, and I was thinking, what kind of research should I start? And the question that we started to ask were, okay, if we're going to interconnect various quantum devices, we don't have them yet, but they will come, just like in the classical internet case. Let's start building the networks. That will tell us where to put the focus on developing new devices. And let's create the same kind of a churn. How do we actually architect the so-called quantum internet? What structure should it have? Should it be a layered structure? Should entanglement distribution be kind of a service that the network will provide? And I've listed here a whole number of questions that I put together for that workshop. And ever since, we've been kind of chiseling away at it, trying to see what can we learn about building networks, quantum networks. Of course, that led to this National Quantum Initiative and then the National Quantum Mission here. At the time, when the funding sources were becoming available to us, we started to think, okay, we need to now create some test beds. And so we partnered with two labs in our neighborhood. I'm in Chicago, and Northwestern University is just north of Chicago. We have two national labs there, Argonne National Lab and Fermi National Lab, that's shown here. And I see some people in this room who work on SQMS, and they are very familiar with this this laboratory. Some colleagues of mine from there, and some from Caltech, and a couple of companies, we started to ask the question: if we were to build a test bed, what should it do? Our goal, of course, was to go beyond point-to-point links. A lot of point-to-point links had been built previously, earlier for QKD type of applications, but then also entanglement distribution. Zeilinger got the Nobel Prize 2 years ago, had this very nice experiment, free space, from La Palma to Tenerife, 143-kilometer polarization entanglement distribution. And then, of course, the Chinese experiments and some experiments in Calgary at the time, distributing entanglement in fiber systems. And this one down here is an experiment at Oak Ridge National Lab. But these are just some representatives. There are several review papers that I can point to. There's tons of these experiments now have been done. But we wanted to do something more. So we were focusing, and here's the Chinese experiment. I'm sure that every one of you have seen this paper here. We wanted to do something more. We wanted to learn about networking aspects of quantum communication. So we architected, or at least on paper, architected a metropolitan scale quantum network, which is to be interconnected with these switches. It has three local area networks, three local quantum networks. One is located at Fermilab, notionally shown here 3 nodes. I think they have 3 or 4 nodes now. And one at Argonne, which has many more nodes that are shown here, and one at Northwestern. And physically, that's how it looks like. The scale is a bit large, but it is metropolitan scale, a bit large in the sense that still the fibers are very lossy. So here is the Evanston campus there. I wish this thing would come back. Here, so here is my lab in Evanston. And we have a facility called Starlight, which is a classical communications hub that connects CERN, the data generated at CERN, the telescopes in Chile, and distributes to all the labs in the US, to scientists at universities. So we have a place in there where we can put quantum hardware. And then we have a connection to Argonne National Laboratory, and then Argonne connects to Fermilab, and there's also a fiber, although this is not available to us, that connects Fermi to Starlight. More recently, so this is an expanded view. We have several different nodes in here, and then this is Argonne National Labs, and this one doesn't show where the nodes are, but the nodes at Argonne are about 3 to 5 kilometers apart. More recently, we have connected to the University of Illinois Urbana-Champaign. That's almost 200 kilometers, much further down. So it's with this backdrop, we've been working towards what kind of issues that we can solve, what kind of issues do we need to address in order to build these networks that someday would interconnect quantum computing hardware. And again, the notion here is that as quantum computers become available, it is likely that the national labs are going to have them first, as opposed to universities or companies in the neighborhood. Although that may not be the case, but at least that was the thinking 5 years ago. So what we call this the Illinois Express Quantum Network, this metropolitan scale network. And we created an architecture for it. Parts of it are being tested now. And we settled on a 3-layer architecture, very similar to modern classical software-defined networks, as opposed to the early OSI models of networking that had 7 layers. So here we have at the bottom the physical layer. This is the physical layer is what where the hardware would be. There'll be all optical switches, different nodes, entanglement, generating systems, transduction devices, and Bell state measurement devices, and so forth. And then, so we've published this architecture, this ISQIC architecture, and this transactions on quantum engineering a couple of years ago. If you're interested, you can look at this paper. This describes the 3-layer model. That intermediate layer is that link layer, and then in applications here we envision entanglement distribution or teleportation as a service that the network would provide. Another important question that we have to address, and that is of the scalability of the network itself. If we scale this network to a larger number of devices, and those devices are connected by fibers, and those fibers need to be dark fibers. Dark here meaning that the only signals they carry are the quantum signals. Then that proposition is going to be very, very expensive. Because even in metropolitan areas, and I'm sure it's true here as well, when you connect from one building to other, you don't own your fiber. Because maintaining those fibers is a big expense, and you usually end up leasing the fiber from a company that owns those fibers and services and maintains those fibers. But from the fiber leaser's perspective, whether you run trickle of photons or you run terabits communications, hundreds of milliwatts of power through those, it doesn't really matter. So the cost they're going to charge you for renting those fibers is going to be the same. That produces a lot of revenue for them by running tens of terabits of communications, classical signaling, as opposed to quantum signaling. So what that tells us that if we want to build quantum networks interconnecting various quantum hardware, then we need to somehow figure out how to leverage the conventional communications infrastructure. Same fibers that will carry classical signals must carry quantum signals. And we've spent the last couple of years figuring that out. And in fact, that is something that we had worked on a number of years ago. back in 2006, actually. This was an experiment my group did, and it was a post-deadline paper at Optical Fiber Communications Conference 2006, long before anyone was thinking about classical coexistence or entanglement distribution. Back then, my group was interested in developing fiber-based sources of polarization entanglement. And so without going into the details, here's a system that produced polarization entangled photon pairs. We multiplexed one into 50 kilometers of fiber that already carried 10 gigabits per second classical communications at the time. That was state of the art back then. Similarly, the other idler photons, the signal this way and idler that way, also went through 50 kilometer spool of fiber, which carried also classical communications. And here's the channel plan. All these wavelengths are on the ITO grid. Two entangled, this is the photon pair channel. And then these are the classical channels, depending on the lasers we had available at the time. And we showed that even after passing through 100 kilometers, that is a signal when demultiplexed out onto a single photon detector, and similarly the idler demultiplexed it out on a single photon detector, had very high visibility to photon interference visibility. As if the classical channels didn't matter. Of course they did a little bit. And notice, I mean, at the time, we had to lower down the powers of those classical channels. 50 kilometers, 10 gigabit per second doesn't really require that much of power, it turns out. But if you want to scale this thing, we need to understand what limits the visibility in these kind of settings. And that's when we started looking at what are the degrading mechanisms in fibers that occur. And predominantly, and I say predominantly because there are other effects that come into play also, it is the spontaneous Raman scattering. Okay, so here is a Raman scattering gain profile of standard fibers, single mode fiber, SMF, and dispersion shifted fiber. Turns out that glass fibers are made of glass. Glass is silicon dioxide. Those molecules vibrate. And as they vibrate, phonons get mixed with photons and upshift or downshift. At room temperature, turns out that you get predominantly Stokes side scattering, which is used in Raman amplifiers in communication systems. But you also get significant amount of anti-Stokes scattering because there's lots of phonons that hang around for the frequency shifts that are involved, or the vibrational frequencies that are involved. And anti-Stokes scattering exists quite far away. And what we decided to do, and in fact, many in the QKD community did this. In fact, these papers that are here, this one from 1997, where this was used first, is in the context of quantum key distribution in the presence of classical channels. So we decided to create our entangled photon pairs in the O band. So this is the scale here is 20 terahertz, and then if you convert that to wavelengths, it turns out that if the C band, the classical channels are in the C band, then the O band happens to be quite far away on the anti-Stokes side, and you don't have very much scattering. And we did a lot of experiments trying to understand, build switches and kind of things to demonstrate quantum technologies which can be used in the presence of classical signals. And so here's a more details of that. So as part of this this work in the last couple of years, we've taken a very careful look at Raman scattering. So for example, what I've shown here is the same plot, but plotted slightly differently. But here now, we are counting. So you send some light into the fiber. These are classical signals, basically lasers modulated at various different wavelengths in C band, in L band, and O band. And then you use filters to figure out how many photons are being scattered. And you plot out curves like this. So the kind of scenarios you have is where your quantum channel is in the C band, your classical channel is in the O band, and you happen to be here, or you can have various different combinations. And the one that I showed you in the previous graph was quantum in the O band. That's our preferred channel plan, classical in the C band or the L band. You end up being here. There's very little photons scattered. Even then, those photons that are scattered, their scattering profiles is determined by what kind of C-band light there is, what classical signals they are carrying. So we need to filter out those in a judicious way so that the quantum signals or photon pairs or whatever quantum signal you have is not filtered out. So one needs to do very narrow spectral temporal filtering so that the quantum signal is optimally filtered. And by doing these studies, we figured out how to do quantum communication in the presence of classical light. Now, that classical light can be somebody else's classical signals, or they could be the signals you need as part of your quantum communication. Early on, I mentioned that in teleportation, you need to make Bell state measurements, and the results need to be communicated from Alice to Bob, those 2 bits of measurements. So that is classical communication. So if one uses the same classical signals to encode those 2 bits of information and use the same fiber to communicate to Bob, then that is multiplexing, and we can use the same network then to communicate that classical signaling. So in that case, synchronization turns out to be an important challenge. As part of this Illinois Express Quantum Network, we did an experiment to demonstrate that you can distribute very high rate entangled photon pairs generated at the Argonne lab generated at the Fermi National Lab and measured at the Argonne lab. That's about 70 kilometers apart. And that required time synchronization. And these fibers, they fluctuate. There are temperature variations, there are vibrations on the fiber, and the timing fluctuates. And what we showed was that by embedding classical signals, you can recover the timing along those 2 fibers, and then use that timing information to synchronize your detectors so that you can do entanglement distribution over that distance with timing resolution on the order of a few picoseconds. So this is again an example of a classical quantum coexistence that allows larger scale networks to be built. Similarly, in another experiment, now we created a photon pair source, in this case a polarization entangled photon pair source, very somewhat similar to the one that's on the Messier satellite, but now utilizing a waveguide geometry and pumping it slightly differently. We sent polarization entanglement from my lab in Evanston to Chicago and back, and we showed that you can do coexistence, that is, you can maintain high quality polarization entanglement while at the same time passing tens of milliwatts of classical power in the same fiber. So that's I'll talk more about this in a minute. The next question, of course, so here's an example of high fidelity entanglement being transmitted over that fiber, and then some results showing the coincidence to accidental ratio as the rate of photon pairs is increased. But again, the point is that's well and good, but can we do something more sophisticated? And that's what led to our next experiment, to demonstrate that not only you can do entanglement distribution in the presence of classical light, but you can take one step further and do teleportation as well. So here's the experiment that we eventually published in December of last year, which somehow created a lot of buzz on the internet. And I don't quite know why, but I can suspect that it has something to do with the fact that we said that it used the same classical signals that are used in the internet. I think just by saying that, somehow it caught on. But nevertheless, the experiment is a landmark experiment in some sense. So what we showed here is that in order to do teleportation, not very different than what Zeilinger had done, not very different than that Tenerife experiment in free space, but done in fibers, or others that have done before, except in this experiment, the entangled photon pairs that Alice and Bob share and the photon that Alice teleports, they propagate in fibers that have a very high capacity internet traffic on it. So, and I'll show them more details in a second. There are two, so the whole experiment is actually in the lab currently. There are two fiber spools, L1 and L2, 5 kilometers, 5 kilometers, and then in the next stage, 15 kilometers, 15 kilometers. Alice heralds a photon in a polarization state, and she uses a photon pair source, not an entangled photon source, but a pair source. And upon detection of one photon, she heralds a photon in a known polarization state. That photon propagates over this L1 meters of fiber, while a transmitter generates a 400 gigabit per second data stream, which is conventionally used in a very high-speed state-of-the-art communication system. That is multiplexed on the same fiber. At this Bell state measurement station in the middle, Alice's photon is separated out and goes to the detector, which is part of the Bell state measurement system. Bob on the other side creates a polarization entangled photon pair. He holds on to one. The other one counterpropagates through this L2 meters of fiber, while the same communication signal is bypassed, launched onto the L2 meters of fiber, and then is demultiplexed out. So that means that Bob's photon counterpropagates that 400 gigabit per second classical communication traffic. Alice's photon co-propagates it, demultiplexed out. Bell state measurement is made, and then Bob analyzes the impact of that on the photon that he has kept. We don't have quantum memories yet, so all of this is done synchronously in the sense that we rely on fourfold coincidence measurements. Alice detects a photon which heralds the qubit, and Bob measures the photon that he keeps. The other two photons become part of this Bell state measurement. So upon measuring three coincidences, we look at what the coincidence of the fourth one is, which gives the measurement of Alice's qubit that she has launched. Okay, so by analyzing these fourfold coincidences, we can determine the nature of the teleportation process. So here's more details of the experiment. It's unfortunately it's quite complicated, but nevertheless I've given you the essential pieces of it. And so again, Bob uses an entangled photon pair source. It's based on a periodically poled lithium niobate waveguide, which is used as an up converter, down converter in a cascaded configuration. Here's the detector that Bob verifies. These are the two Bell state measurement, and there's another detector here that heralds Alice's photon. So by analyzing these fourfold coincidences, you see that irrespective of what polarization state Alice produces here, diagonal or anti-diagonal, and Bob upon coincidences, these are fourfold coincidences, rotates the polarizer in front of the analyzing detector. And he sees these interference fringes, diagonal and anti-diagonal, these two. And then by looking at the visibility of these fringes, we can plot out the fidelity of teleportation, that is, the teleported polarization qubit, what fidelity it has. And irrespective of what Alice prepares, it is above this 2/3 limit. On our average fidelity actually is 85%, plus minus 4%. Again, this is mostly due to the fact that our coincidence rates are relatively low. Fourfold coincidence is here about 120 or so in 300 seconds. Okay, so every 2.5 seconds we get a fourfold coincidence. This was the first experiment that we presented at this European Conference on Optical Communications as a post-deadline paper in 2023. A conference in optical communications, because our goal is to actually take this work into the engineering community. And this was accepted as a post-deadline paper. But of course, when you are rushing to do an experiment to get into a conference, you cut a lot of corners. After the conference, we came back and reanalyzed the experiment and improved the alignment and improved the rates and so forth. We were able to increase by measuring these fourfold coincidences, we were able to optimize the system. Instead of 5 kilometers, we have 15 kilometers, 15 kilometers spools, so that now the total distance is not 10 kilometers, it's 30 kilometers. And by appropriately choosing the right filters and optimizing the filtering, what we show here is that after the filtering, with 18 dBm of power, the residual photon counts on those two detectors, that on all the detectors, is as if they're simply dark counts. That is, you cannot tell the difference between the dark counts seen by those single photon detectors and residual counts that the classical power that's propagating Raman scattering from that. Okay, so by optimizing this, we were then able to extend this work over 30 kilometers. So here is the entanglement distribution in Bob's setup, distributing that entangled photon pair from Bob place to Charlie, 15 kilometers away. It has a fairly high visibility entanglement fidelity. So here's an example of the two vertical and anti-diagonal. And similarly, in fourfold coincidences, the heralded photon and Bob's photon, they need to be indistinguishable. So there has to be a Hongo-Mandel interference between the two. And we show fairly high visibility Hongo-Mandel interference, irrespective of the classical power that's propagating those fibers. And there's a nice dip here. And then we see the same results with 18.7 dBm. That's almost 80 milliwatts of power. And here is the quantum state tomography on that teleported qubit in Bob's possession qubit that Alice launched. And again, the average fidelity is almost 90%. And of course, 30 kilometer, meant that our coincidence counts have gone down a little bit. Now it's about 100 in 900 seconds as opposed to 300 seconds. So this is the work that was published in Optica back in December. And as I said, it had 20,000 downloads in 10 days. So that's somehow this people found that it's very interesting work. And I think it is. So I see that I only have 3 or 4 minutes left. This was an example of the work in the practical sense that we've been working on. But I just want to also talk a little bit about this quantum wrapper networking. This is a protocol that we've been working on. This is work in collaboration with a classical communications person, Professor Ben Yu at UC Davis. And we proposed this networking protocol with a scenario like this in mind, because this is what happens in classical networks. So in classical networks, we do packetized information transfer. You have packets of information that have headers on them, then headers tell the packet where to go, which switch, how do you switch from one place to the other, how do you go from source to destination, and what is the payload that the packet is carrying, and some information on the quality of service and so forth. And I mentioned early on TCP/IP, Transmission Control Protocol, Internet Protocol. But in a quantum network, how do you implement that? You can't measure your packets. You can't measure the quantum information. So you need some way to have the quantum information or your quantum payload go from one place to another. And this protocol is designed to actually embed, that is, wrap the datagram, the quantum payload, packetized in a suitable format with a classical header and a classical tail. This classical is optical bits that can carry destination information. It can carry the type of entanglement the packet is carrying. It can tell where are the entangled partners in the network, and what kind of information is needed to guarantee some quality of service. Or, since the packet is going to be riding along with the quantum payload, can we measure the wrapper bits and infer the health of the quantum bits that are being carried along? So there's a lot that can be done by this kind of a networking protocol. In fact, it can mimic this TCP/IP protocol in some sense, that the headers can tell us what is happening to the quantum payload. Not only tell us what could be happening to them, but carry along important information for providing services on that network, whether that's entanglement distribution or that's teleportation or what have you. So we've been working on this, and some example papers. Again, I don't have the time to go into it. This was a paper at OFC in 23. We've implemented packet switching. That is, you read the header and move the packet to its destination, and then take that header out and replace with another header, because those are all classical bits, so you can manipulate them. And here, for example, the header is in this case we only have one source, but you can place the header here or there. This is the expanded version of it. So this is the visibility measure as the packet is being switched. Okay, so I'm going to skip this thing. This is another piece of work we have, which is the electronic photonic quantum integration, because in the end, these devices need to be made in a scalable form as well. So this is based on silicon photonic devices. The important difference here is that in these devices, the electronic circuitry is truly integrated. So it is the same foundry process that you use for your conventional silicon photonics hardware. I mean, conventional CMOS hardware that you use in your cell phones and everything else. So we've figured out how to actually put micro silicon photonic rings and then combine the two to have an integrated, truly a CMOS compatible integrated system. So here's a photon pair source, which is electronically controlled by the transistors that are on board, and you drive a heating circuitry on the ring and you lock the system so that it produces a fixed photon pair rate as well as a a very high coincidence to accidental ratio. So this is another example of taking these kind of technologies in a practical direction. So I think with that, I want to conclude basically that we've developed architectures, we've done experiments to demonstrate some of the quantum network scenarios that would be relevant. Of course, the devices are limited. We don't have access to quantum memories yet, and transduction devices and our Bell state measurements are somewhat limited, but a day will come that better devices will arrive, and then we should be able to create that churn that needs to happen for quantum networking to move to a stage where they can interconnect computing, sensing kind of hardware. And we're also developing electronic photonic systems. More work, of course, is needed in transduction and repeater technologies, which I briefly mentioned, but there are some hard challenges there. No one really has a working quantum repeater yet, but progress is taking place. The outlook, I've only touched the tip of the proverbial iceberg. There's a lot going on in the quantum space, and I'm speaking here now. Our local neighborhood in the Chicago area, our governor, Pritzker, is a big fan of quantum technologies. And some of you may have heard that the state of Illinois has just invested $500 million in an Illinois quantum and microelectronics park, the south side of Chicago. In the spirit of Daniel Burnham, make no little plans, they have no magic to stir men's blood. Circa 1890, Daniel Berman is the architect who built the city of Chicago. And here's an artist's rendition of the Illinois Quantum and Microelectronic Park. Psi Quantum is our anchor tenant. They are committing to fabricating their million qubit photonic processor here. It's supposed to go live in 2 years. So that's the outlook for the Chicago region. Okay.
Thank you for wonderful talk. It's like we are very close to quantum internet. That's the feeling we get. We are not very far from there. So it's open to questions. 2, 3 questions, not more than that. Yeah.
Let me see if I got it right. In your classical channel carries a 1536 nanometer signal, and your entangled qubits are 1310 nanometer.
A little bit shorter than that, yeah.
A little bit shorter than that.
Yeah.
That's chosen because your Raman scattering is much weaker at that.
Yeah, so I didn't get a chance to explain a little more detail here. So as I mentioned that Raman amplifiers are used in classical communications. So the Raman effect in fibers has been very well characterized, but that characterization has focused on the gain band, which is on the Stokes side. So we know full engineering details of, for a given pump, pumping the Raman amplifier, for a given pump, its intensity and all the properties, we very well understand what the gain band is going to be. And those models, when extended to the anti-Stokes side, tell us how much of scattered, spontaneous Raman scattered photons we expect. But it turned out that that understanding was not fully complete. We found that there's a 13-mode model that one uses to describe Raman scattering in the standard fibers. Turns out there is a 14th peak there. So by the first experiment was done at 1290, and then by going to 1287, the Raman scattered noise was much lower. So we had to very carefully pick the wavelengths. So those are the wavelengths that are.
Why didn't you choose 1287?
That's what we did.
I thought it was 1300 something.
So there is the polarization entanglement. The entanglement is in polarization. The signal photon is 1287. The idler photon is you pump at 1300, so that's about 13 or whatever the numbers are. The two photons at different
Okay, but
wavelengths.
your idler photon and the signal photon are at different frequencies.
Yes, right.
Sir, while designing these metropolitan quantum networks, the one challenge that we of course face is the availability of dark fiber. So that can be addressed through coexistence of classical and quantum signal. Whereas the next big engineering challenge that we practically face is that presence of network elements. Like in presence of network elements.
Okay.
Like in every 50 kilometers, in India, you have to be extremely lucky to have a 50-kilometer fiber without any network element.
Yes.
So how this challenge is being dealt with, and is it the scenario in US different, that you are able to use the existing network infrastructure for 200 kilometers?
Yeah. So I think that challenge is there. So I think there are two types of infrastructure out there. We are using the science infrastructure, right? So there, those network elements, whatever are there, we can go in and fix those. We can create the bypass. So I think it is a while before true integration would occur because you really need to bypass those, right? So, so in our case, we're working with fibers that we have some level of access to them. But certainly, and you know, fibers are getting better. There are hollow core fibers on the scene which will have much lower loss. So yeah, I think these are engineering challenges, but there are workarounds that can be implemented. Yeah.
Okay, let's thank Professor. You can ask. We are running late because third talk is online. The fellow will be waiting, sitting on his computer.
Okay.
So we have to cut start. You can ask during the tea break. I'm sorry. Let's thank Professor Kumar. I invite next talk is by Professor Anirban Pathak. Professor Anirban Pathak is from JP Institute of Information Technology. He works in quantum communication, quantum computation, and all sorts of aspects related with quantum technology. He's part of National Quantum Mission under this quantum computation vertical. So let's listen. Anirban, being a friend, I request you to cut start a bit so that this fellow sitting in London won't be waiting.
So as RP has asked me to finish shortly, and I have prepared many slides, but probably some I will skip, some will just be glimpses. But somehow from morning, this side is inert. There is no question, nothing. And we are also looking at this side, so I'll talk to this. So this is just like there's a landing page, and I'm still learning, and I can even come that side. Good. So primarily, we also work on quantum cryptography. We have a small lab, but we are theoretical physicists, and with time, many things keep changing. So for a few years back, I had a feeling that what we work is quantum cryptography, but gradually we feel that there are other aspects to look into, and understanding is incomplete, and that happens with any subject. So lately, we are looking at many facets of quantum cryptography. So it's not just or many facets of security. So it's not even restricted to communication. So there are certain aspects which are computation, but which require security. And the easiest example which you can think of is voting. So in vote, you need to be secure that who has voted whom. But at the end, you count vote. So that's a computational problem which needs security. Another example is auction. The auction, sealed bid auction, everywhere in India, it happens that you give a sealed bid auction, somebody opens it and tells someone that this is the lowest value, you quote less than that. So if these things can be given security from voting, auction, from quantum perspective, democracy can be strengthened. So security can be taken to absolutely different aspects. And ideas related to security can also be checked from different perspectives. So I'll talk about from a broader perspective, but I'll try to speak a bit about game theory and game theory's use in quantum computing. So thank you. So finally, the control is in my hand. So even so as I mentioned that cryptography has or security has many aspects, and the first slide also show different aspects. So here is a pillar. So in the left there is a pillar, and you can see that this is about a classical cryptography. It's a cryptographer's pilgrimage. So this is in Poznan, and so this are a Polish scientist who break the Hitler's code, and they in their name this pillar is dedicated. But upper side we see quantum cryptography, and the right hand side we see post quantum cryptography. So I'll come to that for quickly for students. So I tell it in all the workshops that algorithm has nothing to do with computer science. Algorithm predates computer science, and any method which solves a computational problem systematically is an algorithm. So perhaps most of us have been taught by an algorithm by our mother when we were taught about that how to do addition. So when you do addition of 2-digit into two and another 2-digit, you only involve 3 steps. 3-digit plus 3-digit is 3 steps. So n digit plus n digit is n step. But if compare multiplication, so if you have 2-digit multiplied by 2-digit as shown in slide, it involves 7 steps. So multiplication is more complicated than, so if we can count the steps, I know how difficult is the problem. So if you count the steps and you find that solving a problem in your method requires, if problem size is n, it requires n square, n cube, n or less than that, log n log n, polynomial or less than polynomial, then we say that we can solve it efficiently. So where you can solve it efficiently, and you take all such problems which can be solved efficiently, they belong to a class called P. Now there are problems whose solutions can be checked efficiently. So I tell you that there is a large number that x is factor of that. You can check that x is a factor or not. So solutions can be checked. So if you can solve polynomial time, then you can definitely check the solution in polynomial time. But opposite may or may not be true. And in fact, nobody knows whether the opposite is true or not. So all such problems make a class called NP. So NP are the problems whose solutions can be checked, but in polynomial steps, but not essentially solved in polynomial. So P is believed to be a subset of NP. So there is no proof. Now people believe that there are problems in NP which are outside P. And if you take such a problem and develop a cryptographic scheme, then you make it bigger. So your adversary will not be able to solve it in finite time, and you can have a cryptographic problem. So for example, most popularly we use RSA, Diffie-Hellman, elliptic curve. So the belief is that your adversary does not have computational power to solve it within finite time till you want to make it secret. So in that sense, it's conditions on the power of adversary. These are called conditional. Now the belief is that, so we were discussing with Manik in lunch that the present belief is that quantum algorithms can solve only BQP complexity class problem. So what kind of problems are they? They can be solved in polynomial steps with a bounded error using quantum resources. And it is believed that BQP is a subset of NP. So if there you take a problem outside BQP from NP and develop a classical cryptographic scheme, and if these conjectures are true, it will remain safe even when a quantum computer is built. And those are called PQC or post-quantum cryptography. It is still classical, still conditional. If these conjectures are true, then it will be safe. So in contrast, we do this kind of schemes. It's called simple BB84. RP had also shown similar things. So Alice prepared 0, 1 plus minus or horizontal, vertical 45 degree, 135 degree polarized photons. Send it to Bob. Bob randomly measures it. So we often write how Bob does it randomly. There is a beam splitter, and one side there is a polarizing beam splitter followed by 2 detector, and the other side there is a wave plate followed by polarizing beam splitter. So the other side with wave plate
is doing a measurement in plus minus basis. This side with only PBS followed by detectors are doing in 0-1 basis measurement. Now, here is a if in the middle. So assume that there is a if not in the drawing. So if can clone the signal, then later on when Alice and Bob are comparing, then if can choose that basis to do the measurement. So we are not, there is no computational problem. You are using no cloning theorem. You are using collapse on measurement. If try to measure and resend, then the state will collapse and create a detectable. But there is something more than that. Quantum mechanics is not probabilistic in a classically completely probabilistic theory. So quantum mechanics is probabilistic when you don't know the basis in which the state is prepared. If you know the basis in which the state is prepared, then it will not collapse to any other state. You will do a measurement in such a way that that state is a basis element in that state, and then a plus state will always be a plus state, a minus state will always be a minus state. So by hook and crook, this spatial basis has to be unavailable from Eve. So for that, what we do information splitting. So in every protocol, this is the case. Whatever, sometime it is quantum and classical piece, as in BB84. So one is the state which is going, and one is the which basis it was prepared. So there is a quantum piece and classical piece. In some other protocol, these are two quantum pieces, like GV protocol. But anyway, now how to look at security? So nowadays we follow Renar's approach. So it was mostly Renar's PhD thesis, and that's have a very big impact on all the theoretical pieces to look at security proofs. And we can quantify the security proof by comparing the real protocol with an ideal situation. So when you implement, there are imperfections and things. So we check that if ideally Alice and Bob must have the same key. Whatever string with Alice, the Bob must have. So K, we calculate that what is the probability that K is not equal to KB, and that should be shorter than a value epsilon, a very small value, and then the protocol is called epsilon correct. Similarly, we compare that epsilon secure. So without reading the detail, means you check that probability that the protocol aborts, because only two things can happen, whether we go to the next step if the errors are less than some limit, or the protocol continues. So now there is a parameter, as I defined in the slide, it's called epsilon secure, and then I define epsilon as epsilon correct plus epsilon secure. Now, as Bhaskar was talking about a network, so there will be something, some CV followed by a discrete variable steps and then another steps. So it is not essential that if A to B is secure and B to C is secure and C to D is secure, then A to D is also secure. So what we need is called composable security proof. So composability claims that if Alice to Charlie is secure by epsilon A and Charlie to Bob is secure by epsilon 2, then we have to prove that Alice to Bob is epsilon 1 plus epsilon 2 secure, then only you can use it in network. So these are not usually discussed, but the security proofs are needed. And as I mentioned that I see it from a broader perspective, and there are several aspects of security. So it's not only limited to QKD. So there are quantum secure direct communication. So where you don't need to generate key, you can communicate directly. And there are a couple of experimental realization. We wrote a protocol on CV, and Bellini and Mato Paris did experiments to realize it continuous variable. And several of such protocols has been experimentally realized by Long and others in Beijing Academy of Quantum Information Science and Tsinghua University. So quantum secure direct communication is without key, and we'll discuss about one such protocol called DL04 because that's experimentally realized. Then there is a protocol called quantum dialogue. So think that tomorrow there is a quantum telephone. So then it will not be only Alice is communicating to Bob, Bob will also communicate to Alice. So such things are called quantum dialogue. And then there are control version of that, control quantum dialogue, control QSDC, and we list some of them, and there is a hierarchy also. So if you can do control quantum conference, which involves multiple people, then you can definitely do it between two people. So then you can do control quantum dialogue. If you can do quantum dialogue, means Alice and Bob can talk and Bob and Alice can also talk, then definitely quantum secure direct communication between Alice and Bob is possible. If you can do QSDC, then you can do QKD, because if you can send a meaningful information, then of course you can see a arbitrary Okay, so if there is a, so my 0 is horizontal and 1 is vertical. So in PBS, if this is 0, nothing happens. If this is 1, after the PBS operation, the second and third qubit swap. So vacuum will always pass. So this 1 is essentially vertical, so it will be reflected, and when reflected, X will remain in X, but when it is horizontal, it will pass, so X mode will come to Y mode. So we don't have enough time to describe, but this is a game theoretic perceptions. So there is a 0, 1, and it's or prepared in either in X basis or Z basis, and then you are sending it, and QTXY is the operation which is confirmed to attack. Alice encodes, and if attacks also from Alice to Bob and Bob to Alice in both sides. And some steps I thought I'll show, but rest time is restricted, but it's easy to follow these steps. So if you can see here that what is happening, that QTOXY 0 vacuum. So we write the entire expansion for this attack. Then there is a Hadamard. So Hadamard is essentially converting 0 to 0 plus 1, followed by a control PBS operations, which is shown in the last slide, and then there is a swap. So we did all the rigorous calculations and ended up with payoffs and this kind of nice plots, which shows that there is no Pareto optimal Nash equilibrium, but there are mixed strategy Nash equilibrium, and there are different scenarios. So what this sub scenarios means, that somebody is using the E1 and E2 attack, E1 and E3 attack, and different attacking scenario, there are strategies are different. But what was most convincing, that in most potent attack is E3, and upper bound for QBR is 14.38. And we have seen that quantum attacks like Pacific attack is more powerful than a classical intercept and resend attack. So different game scenario will give you different payoff, but the message is not that. The message is that game theory can be a beautiful to look at quantum security proofs beyond the usual security proofs which we do, and beyond finite key analysis and such thing. So this is what I was mentioning, that one of our QSDC protocol is implemented by Mato Paris and Javadda and their group. That was a CV QSDC, but the one in which we have applied the game theory is a DV QSDC. So this is in plan that to extend those ideas to a CV scheme. Now, another beautiful tool. Okay, so I'll finish in 2 minutes as is. So another beautiful tool which is useful in extending things beyond QKD, and as my previous speaker was talking about quantum network. So in quantum network, one problem is entanglement routing. So in my last visit to Kolkata also, I spoke about entanglement routing, and here the tools which we use are from graph theory. So I'm not defining graph and local complementary operations, but these are, but what we mentioned, that there is something called bottleneck. So these are, so I'll start from here. So these are grid network. So in grid network, suppose I want to share entangle between 1 and 2 and 5 and 1 and 6, but they are not connected by edges. So what is the minimum number of measurement you have to do? So you need a path. So the path is, normally people take the shortest path. So our protocol says that the shortest path is not always the best path. But here you see, if you apply this path, whatever way you want to go to 1 to 5 and 6 to 1, 4 to 3 will be in the common. And this is called bottleneck. So our question was, if we extend the size, can we remove bottleneck? So then we introduce the local computation, sorry, local complementary operations, LC1, LC2, LC3, and this opens up and convert a 2 cross 3, 3 cross 2 network into a ring network. And then you see that in this ring network, these are not connected. Okay. So bottleneck problem is solved. However, we could not solve it in a butterfly-like network. In this network, we could not solve. So eventually, we have seen that when it is odd times 2, it is solving, but when it is even times 2, it is not solving. But there is no proof. So then, to generalize it, so these are relatively new results. To generalize it from larger network, the 3 cross 3, 4 cross 3, if we don't use a extra, if we don't use the shortest path, whether there is a benefit or not. So we have seen that So these are the number of bottleneck which shortest path algorithm cannot remove and what our protocol can remove. So if it is a 6x6 grid network, sometime it can remove 125 extra bottleneck also. So then referee asked us how it increases and how many extra path, means like shortest path has 6 nodes, 6 edges. So we added up to extra 6 edges. So how it is improving with the addition of edges. So this one is showing that if we add additional 1 edge, 2 edge, 3 edge, 5 edge, how many possible connections are now bottleneck can be removed. So one means 100%, any point to any point entanglement routing is possible. So this shows that how it grows with addition of edges, but computationally the problem increases with the addition of edges, means addition of extra length in the path. So final message is that game theory, graph theory, these are not the conventional tools to look at the quantum network and security, and at least graph theory was more used, but game theory is a new technique and that can help you to have a new perspective to security. So far we have started DL04 protocol and DV protocols only. We want to extend it to CV, etc. So I will stop here.
In time, yeah. So one or two questions, otherwise we can.
Thank you for the interesting talk. About the authentication essence.
About?
The authentication essence. Well, quantum or classical, essentially when in a network they have to welcome a new user, essentially there is a need of essentially for the new user to show credential in a way. And apparently there is no difference between the two. And in the quantum section, then possibly QKD may take care of what is needed extra. This is also something you can extract from that paper in the archive of Renato responding to NIST say, accusation that is quite on point. So do you agree with this view? Essentially,
No, I partially agree, because there are classical schemes as its own loophole. But then in addition to that, there is a foundational question also that quantum cryptography can be fully quantum or not. So our answer also is that it cannot be fully quantum. So some classical shade will remain in the authentication path, but the authentication weaknesses can partially removed with this quantum identity authentication, because these are also schemes and they do have security proof and they have vulnerabilities. So this is now a big interest of the security proofs of identity authentications, but there is no experiment on quantum identity authentication so far. So these are theoretical protocols so far. So either as a,
when you show the credential, no?
but it can be a shared entanglement also.
Yeah, well, yeah, you can choose, but that part is needed. Otherwise,
yes, but if that part is only considered, then they are equivalent. But then the question is how rest of the things are done. So,
and you say that if you have this say pre-shared secret in quantum terms as well, QKD is not enough.
No, QKD is only one path. Means then QKD also amplifies, but you can use QSDC. You can use, there are many paths, and these paths can be compared and quantified. There's not a unique way. QKD is not the only way.
We can take one question, yeah.
Sir, which qubit is more safer, photonic qubit or superconducting qubit?
So, no, as far as cryptography is concerned, you cannot use superconductive qubit. So, when you are communicating, you have to send it from one place to other place. You cannot carry your dilution refrigerator from here to another place. So, it's all quantum communication things are all photonic qubits.
Okay.
So, in photonic, you can have different degrees of freedom, whether you are encoding it in polarization degree of freedom, in another degree of freedom, but it's always photonic.
So, because we in QKD we know that the some percentage of reliability means there is some percentage of insecurity is also there.
Some percentage of
insecurity in communication is also there.
No. What do you mean percentage of insecurity? I mean certain things will be lost. There will be channel loss. Like in our security analysis, we also schemes that there is a noisy channel, but Eve replaces the channel with a perfect channel. So if anything happens, that's due to Eve. But then there is an upper limit. You can calculate that under this error, this is the maximum qubit error, q bar, which I can tolerate. So if the q bar become after that, then we drop. So that's what we were saying, that there can be two things, that I go to the next or I stop communication after this means. So we know the upper limit up to which error we can tolerate. So if it is beyond tolerable error limit, then we don't go in the next step. And since distributing key, we are not distributing message. So when we know that there is a Eve and beyond that limit, we don't use that key. And there are post-processing techniques. So
Okay, thank you.
Hope online speaker is connected already and he is waiting. He's there already. So we can just project him and then we can introduce. It's thank Anirban by the time. So our next speaker is from Professor Jonathan Oppenheim from University College of London. Let him come on.
Hello, can people hear me all right?
Yeah, we can hear you, but we can't see your.
You
Sure.
can't see me. Ah. There, can people hear and see me now?
Yeah, we can see you now.
Okay,
Thank
great.
you. Thank you for waiting. Sorry for being late. So our next speaker is Professor Jonathan Oppenheim from University of College of London, and he has worked extensively in quantum information theory as well as quantum gravity, and very good work in quantum thermodynamics. So without wasting time, let's listen to Professor Oppenheimer. What he's going to talk about today. Yeah.
Great. Yes, thanks very much for inviting me. I'm really sorry I can't be there. I have very fond memories of Kolkata when I last visited, and hopefully I will be able to visit some other time. I'm happy if people want to ask questions during the talk, in which case I won't be
Hello,
able to.
Professor Oppenheim, we can't hear you. Just hold on. We can't hear you clearly. Please arrange something.
Right.
And we can't see the slides also. Can you share the slides and all? Or we can't see. We can't see the slides. Are you having slides there? Yeah, now we can see the slides.
And can you hear me all right?
No, this is not the slide. Yeah, this is his slide only. Yeah.
Do you see the first slide?
Visible top and astrophysical test of the quantum nature of space-time. That's your slide. Yeah.
Yeah, that's right.
So we can see that, and your voice is not very clear somehow. I don't know.
I'm not sure what I can do about that.
Can you increase the volume of your speaker? Or...
Let me try that. One moment.
It's a local problem. Yeah, Muller says that it's local problem.
Do you think it's local?
His problem is at TCG. That's what he's saying, Muller.
How's that? Is that better?
Yeah, it's fine. Yeah, it's fine now. Yeah.
That's better. Okay.
Yeah, it's better, much better. Now, slides you can display and start up. Yeah, please share the screen and then you can start. Yeah. Thank you.
Okay. Great. There we go. So I was just saying, I'm not sure if it was heard, but I was just saying I'm very sorry I can't be there, and hopefully I'll be able to come again. I was visiting there a couple years ago and have very fond memories. I'm also happy just to say that I'm happy to take questions during the talk. So, but I won't be able to see you. So if you want to ask during the talk and you're able to get a hold of the microphone, then just interrupt me and ask. I'm very happy to take questions throughout. And that's because I think that's important, because this is very much a mixture of quantum information theory and gravity, and no one really is an expert in both these areas to a sufficient degree. So it's liable that there will be places which are puzzling, and I'm happy to take questions that are puzzling to me as well. So this is joint work with a number of my students. And in particular, the work I'll be talking about mostly, which is these experimental tests, is joint work with Zach Weller-Davies, Barbara Skoda, and Carlos Brecchieri. So the question that I'm interested in is a very basic and fundamental one. It's just this question of whether we can consistently combine quantum mechanics and classical mechanics. And these are really the only theories we currently have. But they are formally very similar. So in quantum mechanics, you have the density matrix sigma. It evolves according to the Heisenberg equation with the commutator of the Hamiltonian. And in classical mechanics, we have a probability density rho, and it evolves in a very similar equation via the Liouville equation, as well, given by the Poisson bracket with the Hamiltonian. And so I can imagine I have a particle which lives in phase space, Q and P, and a quantum system which lives in the Hilbert space, say a two-level system psi. This is the two levels of the system living in the Hilbert space. And I might ask whether I can make this classical particle and this quantum particle interact. And we do this all the time in one direction. So we often have a classical system which acts on a quantum system. So for example, I can turn the knobs on my magnet or my potential and cause the quantum particles to move in a particular way. Likewise, in a double slit experiment, the box and the slits and everything is classical. We treat classically. So that's fine. But the harder problem is whether we can have a quantum system which back reacts on a classical system. So that's the back reaction problem. And it's one I want to address partly just from a foundational point of view, whether it's possible just mathematically to have a quantum system back react on a classical system, but partly because I'm interested in gravity. And in gravity, we only know how to treat space-time. So gravity, the theory of gravity is general relativity. It's our theory of space-time. And we only know how to treat space-time classically. And that might be just because from an effective point of view, it's the only way we can do it. But also maybe fundamentally, maybe space-time is fundamentally classical. And there are reasons to believe that might be true. And that's because even posing the initial value problem in gravity is problematic if space-time is not classical. So if space-time is quantum, usually when we do field theory, we specify field theory by imagining some quantum fields which live on a space-time, and we impose the commutation relation, for example, that psi at x and psi of y should commute. But if we don't have a classical space-time, then we don't know how to do this, because we don't know whether our space-like our surfaces are space-like or time-like. And so we can't really even define, we don't know at least how to define a quantum field theory if we don't have a classical space-time. So, there's this picture in which you have the regular quantum forces in this arena of space-time, and the space-time gets curved. That's what gravity is. And it's because gravity is the only force that can that is described in terms of space-time geometry, it's not even really clear that we should really think of it as a force in the usual sense. And in fact, gravity is not a gauge theory in the usual sense. In a gauge theory, you act a gauge transformation on the fields psi or phi, and the gauge transformation acts on the fields at the point x, whereas in gravity, the symmetry is that we move the points x themselves. So gravity is very different from the usual gauge theories that we use to quantize. And so because of that and a number of other reasons, it's very questionable whether we should be attempting to quantize gravity. Maybe more to the point, we don't have a quantum theory of gravity at the moment, and we have no experimental evidence that gravity really is quantum. And so I'm going to be advocating that we should be experimentally testing this question. Are there any questions at this point just about the motivation or the problem?
You go ahead. Yeah, we can ask question at the end. Yeah.
Okay.
Go ahead.
I mean, I do enjoy interruptions. Okay, so let's discuss the implications. What I'm going to do is just make a simple postulate, which is maybe gravity is classical, and if it is true, it has a number of interesting implications. One is that the Born rule and the measurement postulate are not needed. So we will find that particles in superposition have to automatically localize with probability distribution given by the Born rule. So we don't need the measurement postulate. So that's one of the immediate implications of stating that space-time should be fundamentally classical. The other interesting thing is that the theory is fundamentally renormalizable, meaning that it holds down to the shortest distance scales. And interestingly, that is not true of quantum gravity. So famously, quantum gravity is known to be non-renormalizable. And so you immediately solve this issue if you imagine that space-time is classical. There are a number of other implications which I'm interested in. For example, the black hole information problem has an easier resolution, and this theory could, there's evidence that this theory would solve the cosmological constant problem and would look very much like the dark matter. So we probably would not need dark matter if this theory is true. Or I should maybe say we may not need dark matter if this theory is true, because there are a number of tests for dark matter which we're not yet sure if this theory can reproduce. Good. So let me just say that for a large part of this question of whether we can have consistent classical quantum dynamics, there's been a huge debate in the literature. So quite a lot of people have claimed that we cannot consistently couple classical and quantum systems. There have been some indications that this might not be true, but in some sense, this has now been settled. There were some early examples of consistent classical quantum dynamics in the early 90s. And we now, in fact, know the most general form of this dynamics. And we even have these experiments. Now, so what I'm going to talk about is the following. I'm going to discuss the most general form of classical quantum dynamics, and then I'm going to discuss the experiments to determine whether gravity is classical or quantum. I probably won't get to these other topics. So what is the most general form of dynamics? And if you're familiar with master equations, I think you'll find this interesting. So remember that we have, for quantum systems, we have the Heisenberg equation for the density matrix sigma. For classical mechanics, we have the Liouville equation, and now we want to combine them in some consistent ways. There's a number of ways we can do it. One is this master equation approach, which is what I'll be discussing, and we can derive its most general form. We also have a trajectories approach and a path integral approach. So the way we're going to describe this quantum system and this classical system together is via a density matrix for the probability density, I should say, sorry, for the classical system. So the classical system has a probability of being at a particular point in phase space, and this is given by rho of Q of P. So there's some probability distribution that you find the particle at some point in phase space. And then given that you find the particle at this point in phase space, for the qubit at least, you have some probability that the qubit is a 0, some probability that the qubit is a 1, and some coherence. And all these things, the probability of finding the qubit in the 0 or 1 state and the coherence, they depend on where you are in phase space. So that is how we describe the classical quantum system. And just like we have a normalized density matrix for quantum mechanics and a normalized probability distribution for classical mechanics, we should demand that the classical quantum state is also normalized. So the classical quantum state should also be positive, just like in quantum mechanics we have a positive matrix, and in classical mechanics the probability distribution is positive, and it should integrate to 1. So if we take the trace of the classical quantum state and integrate over phase space, that should equal 1, because probabilities have to always sum to 1, and because probabilities are positive, then this object should be positive at any point in phase space. So that's the condition on the classical quantum state. And you can even write it as, you can write the classical quantum state in a purely quantum way. For example, we have some probability of being at a particular point Z in phase space in the classical, for the classical system, and then conditioned on being at a point Z in the classical subspace, the classical phase space, we have some quantum density matrix. So that's how we can describe a classical quantum system, and we can embed that in a fully quantum system if we want to, although whether we can do that for all times is probably doubtful, but we can do it at least initially. And now you probably recall how we derive the Lindblad equation for open quantum systems, or the Liouville equation, or the Fokker-Planck equation for classical systems. You really just demand that the state, the classical quantum state, must be positive, and so the dynamics must be completely positive, and it must be linear. And in this way, we know that it will preserve probabilities and the statistical interpretation of the density matrix. And so we can use this to derive its most general form. So I'm going to give you the most general form of this interaction, the classical quantum interaction. But before I do that, I will give you just a very simple example, which is a Stern-Gerlach. So imagine we have a spin half particle, and we have a magnetic field, and we have a free particle. So the p squared over 2m Hamiltonian plus this interaction between the spin and the particle. And so if the particle is spin up, then we expect that the particle will be forced to go up. And if the particle is down, then its momentum will decrease and the particle will be pushed in the other direction. So if, and I guess the interesting question is, what happens if we put this particle in a superposition state? What do we expect to happen if we turn on this classical quantum interaction? And so here's the dynamics that you can show. This is just a simple example. And you can see that you have all the kinds of dynamics we saw initially. So we have that this classical quantum state, or the quantum part, evolves according to the Heisenberg commutator. And then you also have this Poisson bracket for the classical evolution. But note that there's an operator ordering ambiguity, and so you could have the Hamiltonian could be on the left or the right. It matters whether it's on the left or the right of the density matrix, and so we take both options and divide them by 2. This is called the Alexandrov bracket, and then you have you can prove that in order for the dynamics to be completely positive trace preserving, you must have some diffusion, some Fokker-Planck-like dynamics, diffusion on the classical system, and you must have some decoherence on the quantum system. So you can prove that any consistent classical quantum dynamics has to have both diffusion and decoherence. And in fact, you can prove that it has to, in order to satisfy complete positivity, it has to satisfy this inequality here. And that's what we're going to be using to test the quantum nature of spacetime. We're going to use the fact that this inequality has to be satisfied for any theory in which spacetime is classical or quantum. So what you can show in terms of what happens is that if I have a particle which is initially in a superposition of up and down, then it will essentially act diffusively, so it will jump around and you won't be able to tell whether it's going to be going up or down, be pushed up or down, but eventually it will. And what's remarkable is that throughout this process, if a certain condition is satisfied, if the inequality is saturated, then the quantum state will stay pure throughout the evolution. So the quantum state will, instead of collapsing or decohering, conditioned on the classical trajectory, the quantum state stays pure and essentially stays on the surface of the Bloch sphere and will either collapse to the 0 or the 1 state. I could take questions at this point if you want me to, or if that's possible, or I could go on to the experimental tests.
Let me ask the audience whether anybody is having question. Anyone you want to ask? Yeah.
I think I'm audible. So this is a question on Dioc's theory where there was diffusion in the equation and there were quantum and diffusion was there in 1995 paper.
Yeah.
And also in Gisin-Percival equations, it is some non-linear Schrodinger equation. So same, there is diffusion as well as a quantum evolution. So how do you say this is different?
So good. I don't know the Gisin paper, but if it's nonlinear, then if it's nonlinear, then we would reject that as a theory because it doesn't respect the statistical interpretation of the density matrix, and it leads to things like superluminal signaling. So we are insisting that the evolution be linear. Now, the Diocchi example is, I think, a beautiful precursor, I would say, to our result, because so Diocchi gave this example of a constant force master equation, and he, I think, was the first one to really notice that you could make it completely positive if you satisfied this inequality. And so what we've shown essentially is that this kind of inequality has to hold for any theory which is consistent. So it's not just a matter of a particular example, but it has to hold for any theory which consistently couples classical and quantum dynamics. And that means that we can now go out and use it as an experimental test for the quantum nature of spacetime, because we know that if spacetime was classical, it would have to satisfy this inequality.
So I just want to add a comment that this nonlinear Schrodinger equation is stochastic. So because it is stochastic, it doesn't have any superluminal. There were discussions and it's resolved. I just wanted to get it clarified from you that diffusion.
Oh, I see. Okay, so you mean it's nonlinear on the trajectory, but if you sum over all the trajectories, then it leads to a linear. It's linear in the density matrix.
I have a question.
Yeah.
Does your system of this classical and quantum superposition, I may say that, it transform into the classical and quantum? Will this will reduce to the pure classical system or a quantum system? What is the limit for that? How can we reduce it from classical quantum system to purely classical or purely quantum system?
Oh, I see. So yeah, so you can so maybe this is another one of the differences between so this is if you integrate out, for example, the classical system, then you don't get a Lindblad equation on the quantum system, and that is because you have two coupled systems, and so the theory is non-Markovian. The classical system serves as a memory if you integrate it out. So this is maybe another way in which it generalizes a number of previous results, like the Dioschi evolution. Likewise, if you integrate out the quantum system, it will not look like Liouvillean dynamics because the quantum system serves as a memory for the classical system. So it's only if you have both systems that you have a Markovian dynamics. Now, maybe your question is about the case where you imagine two quantum systems and you take the limit where one of them is classical. And in that case, we have shown that our dynamics, there is a parameter space where you can think of our dynamics as as genuinely the limit of taking one quantum system to be classical. But there are also parts of the dynamics which don't appear to be the result of that. So in other words, there is a part of the parameter space where this can be considered as an effective theory when you take the classical limit of one system while it's interacting with another system which remains quantum. But there's also a parameter space where we have to treat it as fundamentally classical. Does that answer the question?
Okay, please carry on. You have 10 more minutes, Jonathan. Yeah.
Okay, great. Okay, so that's the dynamics. And now that we have the most general form of this dynamics, I guess the nice thing is we can now apply it to general relativity. So we've done that. We've applied it to the fully relativistic theory. And I'm not going to really talk about that because the master equation looks rather complicated. But what instead I will do is just talk about the experiment. And so let me explain what the experimental proposal is. And I will give you maybe an intuition about why we have to have this trade-off between decoherence and diffusion. So let's imagine that we have a particle which is in a superposition of being here and there. So it's in a superposition of here and there. And we imagine it's a massive particle, so we can turn on gravity. And remember, here we're going to treat gravity classical. So gravity is going to be, space-time here is going to be in a definite state. So it'll be in a definite state depending on whether the particle is here or there. And so this is in some sense why there is an apparent contradiction between treating space-time classically, which is that if you have a superposition which is not in a definite state, and then space-time has to be in a definite state, it doesn't really know where to be. And in fact, we could measure the gravitational field to arbitrary accuracy to determine whether the particle is here or there. However, if we add stochasticity, if we add randomness to space-time, then measuring the gravitational field will not determine whether the particle is here or there. So we imagine adding a lot of noise to the gravitational field, and then it will be impossible to measure whether the gravitational field is here or there, at least initially. But the thing is that we can, collect data from the gravitational field. We can just sit there and measure the gravitational field, and eventually we will learn whether the particle is here or there. So we imagine sitting here, with a pendulum measuring the gravitational field. We can imagine that there's someone at every point in space-time who's measuring the field, and they eventually measure the field to enough accuracy and collect enough data that they learn that the particle is there. And so this in some ways is the trade-off. If we want to have particles which are in superposition for a very long time, then the amount of noise or randomness or stochasticity, it has to be very large in order for us to keep the particle in superposition, because if it's not large, then we would learn very quickly that the particle is there. If the amount of noise is very large, then it will take us much longer to figure out whether the particle is here or there. let me give another kind of example to get the idea. So imagine the double slit experiment. Although we're going to perform this double slit experiment with large particles which have mass. And if the particles have mass, then we can use a pendulum or a gravitational wave detector to figure out which slit the particle went through, because if the gravitational field is classical, then we can measure the gravitational field to arbitrary accuracy, and we can go very close to the particle and measure the gravitational field, and we won't disturb anything. And so we can measure which slit the particle went through without disturbing the system if the gravitational field is classical. And that will contradict the fact that we see an interference pattern at the screen. And so that is a contradiction unless there's a lot of noise in the gravitational field and we cannot measure which slit the particle went through. So we can imagine that we measure, you know, the trajectory of the particle coming from the slit to very accurately, and we eventually learn, you know, which slit the particle went through. Note that something that is maybe a little bit confusing is that the electromagnetic field will also be different. So here E is the electromagnetic field. It is also different depending on whether the particle goes through the left slit or the right slit. The difference is that for the electromagnetic field, the two different states of the electromagnetic field are either not orthogonal, so they have overlap, or it can be the case that we have a highly entangled state between the particle and the electromagnetic field, but this gets undone when we finally get to the screen. So those two things mean that the electromagnetic field does not have to satisfy this trade-off between decoherence and diffusion. It's only if you have a classical system that it has to satisfy the trade-off, and this is the more general form of the trade-off which holds for all classical quantum systems. And so, you know, here we imagine that we have the distribution of the gravitational field, and it's different depending on whether the particle goes to the left slit or the right slit. And depending on how strong the back reaction is, these two peaks will move further and further apart, faster and faster. So if the back reaction force is very strong, then we're going to need a lot of diffusion, which is the spreading of the wave of these packets. It has to spread a lot in order to have a very large coherence time. So this is the trade-off in simpler terms. So it's a trade-off between the coherence time, the level of diffusion, and the gravitational force. And so what we advocate doing, so here, you know, the bigger the force, the further apart these two classical probability distributions will be. And so you will need a lot of diffusion, D2, in order for you to not be able to distinguish these two peaks and for the coherence time to be short. So what we're advocating is that we do double slit experiments to place constraints on the coherence time of large molecules. We also do precision Cavendish experiments to put an upper bound on D2, and then we use the trade-off to squeeze the theory from both sides, and we could potentially rule out any theory in which gravity is fundamentally classical. And what's nice is that we, for example, if we see noise in the Cavendish experiment, that is fine. We don't need to decide whether it's attributable to gravity or whether it's attributable just to noise in our equipment, because no matter what the source of the noise, it puts an upper bound on D2. And likewise, in these double slit experiments, we don't need to decide if the decoherence is due to gravity or the environment or something else. We just need to put a bound on the coherence time. So that's what's nice about this experiment. We don't need to decide what the source is of the noise in either experiment. We just use it to put a bound, and that will allow us to rule out a classical spacetime. Or if we found that find that the bound is saturated, then that would, I think, be very strong evidence towards this post-quantum theory of gravity. So we propose doing these with quantum technologies. precision Cavendish experiments, such as the LISA Pathfinder experiment, or double slit experiments like the kind that Marcus Arendt does in his lab. And there is a small bit of freedom. If you, we think now that if you demand Lorentz invariance, there's actually no freedom whatsoever. But if you don't care about Lorentz invariance, then there are different theories. If you care about Lorentz invariance, there's only one dimensionless coupling constant, which you can bind from both sides. And current experimental bounds are within maybe a few orders of magnitude, and we believe that we can test this in the near term. So let me just end with mentioning some of the challenges. So the theory, we still don't know. There's still some sanity checks we're doing to the theory. There is some tension, for example, there may be at least between the theory being completely positive trace preserving and covariant. We have a covariant theory, but we haven't shown that the covariant theory is completely positive trace preserving. We have another theory which is completely positive trace preserving, but we don't know if it's covariant. And we're not even sure if these two theories are identical, et cetera, et cetera. So there are a few kind of outstanding sanity checks that we still have to go through. But at the end of the day, I'm kind of positive because this thing is experimentally testable. So is spacetime classical? I have no idea. I don't get very good odds. I mean, I get great odds from my point of view, but most people tend to believe that spacetime must be fundamentally quantum. I'm less sure because we have this consistent theory, and we don't really yet have a quantum theory of gravity. So the main thing now, I think, is to test this theory experimentally and also check that this the general relativistic version of this theory passes a number of sanity checks. So with that, I would like to thank you for your attention, and I'm happy to take any questions.
Thank you. Thank you very much for giving a talk on this very fundamental question regarding space-time and quantum mechanics. So we have question, yeah.
Yeah, hi, Jonathan. Very nice talk. So you mentioned at the beginning that your master equation approach is one of the possible approaches of dealing with this problem. And two others I think you mentioned are one to do with the trajectory approach and the other, the path integral approach. Now, do you expect such consequences like this trade-off to persist in such approaches as well? I mean, what are your comments?
Yeah, so the trajectories approach is equivalent. So so that approach, you have the trade-off as well. So in all these approaches, the trade-off we've proven it's a feature of every system in which you treat one system classically. So in this regard, you expect the same thing. The path integral and the trajectories are just different formulations. They must be equivalent in some way. But I guess the path integral is the one where we're the least sure because we haven't been able to derive the most general form of the path integral. The other thing maybe I can also say is that in all of these systems, we haven't really there hasn't been much exploration of even just simple examples. So we've recently done a quantum oscillator interacting with a classical oscillator. And as far as we know, that's the first non-trivial system that people have really looked at. And so there's a lot of scope for looking at toy models of these systems. And for that, there's some systems which are easier to look at in the trajectories picture. So that's, I think, a lot of people that do quantum measurement and control are very familiar with that kind of framework. And so that may be one where it's maybe easier for people to understand the formalism.
I have a more technical question, a more general one. The technical one, you were saying that GR is not a gauge theory. I think you were referring to diffeomorphism invariance, right? And I would agree with that. But my understanding is that if you instead look for Poincaré gauge, local Poincaré transformations in the tetrad formalism, it can be seen as a gauge theory. Is this...
So people often say, yeah, so the reason people often say that it is a gauge theory is because of the tetrad formalism. So you can recast GR in the tetrad formalism.
Right.
It then has a local SO31 symmetry, which looks very much like a gauge theory, but
Right.
that is just a symmetry of the fact that you've written it in this particular way. In addition to this gauge symmetry, you also have the diffeomorphisms.
Yeah.
So, you can write it so that you also have a gauge symmetry. So that there is also a gauge symmetry, but that's not a symmetry of the theory. That's just a symmetry of the particular way you've just chosen to write it using the tetrad formalism.
I see.
And in addition to that, it also has this diffeomorphism. So that is why sometimes people, I think, claim that it is a gauge theory, and I think that is a misunderstanding actually, but it's something that's claimed quite a lot.
Okay, I see. Thank you. And regarding the other question regards the what would be, I mean, I would imagine that if you have a particle in a momentum eigenstate, which is spread out all over the place, then you would have very big decoherence, right? Because very fast decoherence, because it's like a superposition of a particle being everywhere. It's a plane wave. And in that case, maybe one test you could do for your theory would be to look at uh, particles coming from outer space and look and do a momentum measurement on them. I mean, you would expect that they would be decohered in the momentum basis, like a neutrino coming from a distant quasar. I mean, it's been going on for years, and you would expect that it would have decohered, no?
So I think it is true that if you have the theory doesn't predict that momentum eigenstates will get the decoherence should be fairly slow on such a state, because it does turn out to be very closely related to how dense your wave packets are. So in fact, the example you gave is the one where you would expect the slowest decoherence. So what we found interestingly, there are other theories in which you have decoherence, for example, the Dioschi-Penrose proposal. But in this theory, it turns out that what becomes very important is this wave packet density. And so a momentum eigenstate would actually collapse incredibly slowly. What collapses quicker is if you have a superposition of two particles in where the left branch and the right branch are highly peaked. And that turns out to give you the fastest rate. And so because that's not really what people test, we are actually have high hopes that the bounds can be improved dramatically. And so that's what we're advocating for people who are doing coherence experiments, that they look at this case where you have these two superpositions which are very highly peaked.
Okay, I see. Thank you. Thank you.
We can take one more question. Anybody having? If there are none, then let's thank the speaker. Thank you, Jonathan, being
Thanks
online.
very much.
Thank you.
Thank you.
So we can break for 15 minutes for tea, and then 5:15 we should be here. Yeah. Thank you. I don't know whether we should wait for others to join or it's time anyway, 5:15. We are running late. We have to close also. There are three talks again after the tea break, half an hour each. And so we can start, I think. First talk in this session is by Dr. Professor Siddharth Das. He is at Triple IT Hyderabad and works on quantum information theory related with quantum communication also and quantum communication. So let's welcome Siddharth to give conditional entropy and information of quantum process. Yeah, Siddharth.
Am I audible? Okay, I think I am. Yeah, so I'll be talking about conditional entropy and information of quantum process. Yeah, so I'll be talking about conditional entropy of quantum process. Most of you have already heard about entropy of quantum states, entropy of random variables, conditional entropy of random variables, conditional entropy of states. So this is going to be extension of these information measures or entropic measures from states to the channels. And why do we care about it? So the conditional entropy of state has been applied almost everywhere, and the basic quantities of information theory are entropy, conditional entropy, mutual information, conditional mutual information. So that is why we care. So there is both physical aspects to it, because as communication aspects, conditional entropy is instrumental in QKD or like anything. Yeah, I mean information. If you think about information theory, then you think about entropy and information measures. So that is the idea or the motivation behind it. Yeah, so I mean, there is long quest to understand quantum processes. Information theory is powerful tool in analyzing potential of quantum systems. So, and also a question is that could it possibly unravel novel information processing features of quantum processes? Yeah. Now, regarding the conditional entropy, so before, I mean, since so far there has been no definition of conditional entropy for quantum processes. There is entropy for quantum process, but not conditional entropy. So the question would be, how novel would the conditional entropy of quantum process be when we compare this with conditional entropy of state or entropy of quantum channel? Can the conditional entropy of bipartite quantum process be strictly lower than the least possible value of conditional entropy of quantum state or entropy of quantum channel? And then if yes, what would the signature property of quantum process be? So why are we asking these questions? It will be clear in the next slide if you see. Okay, so okay, before coming here, the entropy of random variable and quantum states both are non-negative and upper bounded by the log of dimension of the system. It is conditional entropy of quantum state which can take negative value and was counterintuitive classically, because classically you can never have negative conditional entropy. However, because of entanglement, which is purely quantum correlation, you can have negative conditional entropy. And what do you mean by entropy? You may understand in simple way that the entropy is uncertainty, the measure of uncertainty, and conditional entropy is measure of uncertainty of a system when you have access to the correlated system or some other system. So for the bipartite system. Yeah. We have heard a lot about quantum states channels already, so I'm just going to do a brief recap. In quantum information theory, quantum states are described by density operator, which are positive semi-definite operators, that is matrices with positive eigenvalues, and the trace of eigenvalues is equal to 1. The sum of eigenvalues is equal to 1. And quantum channels are completely positive trace preserving maps, which you may have heard in the previous talk by Jonathan Oppenheim. Yeah, so these are completely positive trace preserving maps, and you can generate, like any quantum channel will have this strain spring dilation part where you have acting joint unitary on your system uncorrelated with environment, and then you trace out some degrees of the freedom. And the transformation of quantum channel is given by quantum super channel, which can be written as concatenation of quantum channels to the channel. So any quantum super channel can be written in this form. Everything is quantum channel. When I'm saying everything is quantum channel, even density operator or quantum state, you can think of as a special case of quantum channel. Quantum instruments, measurements, anything. So it makes sense to discuss or to understand the information theoretic aspects of the quantum channel itself. And whatever is, like let's say you have function of quantum channel, entropy measures of quantum channel mutual information. From this, you should be able to derive also for states, because the states are a special case of quantum channels. Yeah, so now looking at this, so why are we interested in this conditional entropy? It says something new. So conditional entropy of quantum state said something new, that it can be negative, and that was because of entanglement. So what will the conditional entropy of channel gives us? So what about the lower bound and all? So here if you see the upper bound for both quantum, so these are for quantum states and channels, entropy and conditional entropy, upper bound for both are log of dimension of the system, non-conditioning system, whereas they differ in the lower bound. They differ in the lower bound. So here the entropy of quantum state can be written as Shannon entropy if we are looking at the spectral decomposition of the density operator. Whereas conditional entropy, it can take negative, and this was the deviation from the classical. So conditional entropy, I mean, in the true sense, says something about the quantum phenomena. Entropy of the quantum channel has same lower bound as entropy of state, conditional entropy of state, because entropy of channel can be recasted as conditional entropy of the output of the channel with rest when you optimize over all possible inputs to the channel. Whereas the conditional entropy of channel, I'll come to the formula that we have formulated later on, but is however very distinct from the conditional entropy of the entropy of the quantum channel. And this is already a demarcation or deviation from what we have. So the conditional entropy of channel in this sense is already saying something which is not captured in the entropy of channel as we would have expected. And why is this? Yeah, so here we'll be doing conditional entropy. We'll be seeing what we get in quantum states versus what we get in quantum channels. So the entropy of state is minimal if and only if state is pure and the value is 0. Whereas entropy of channel achieves minimal value, which is minus log of dimension of the system, either it is input or output, depending on whether you have in isometry or unitary, if and only if channel is isometric. If channel is unitary, then you can just take minus log of the dimension of k, which is output of the channel. So here channel is from A prime is input and A is the output system. So these two results are known. I mean, yes, so this gives the reference. So this is not our work. If you don't see the reference in this slide, in this particular slide, then that is our work. So the conditional entropy can be negative, and that implies the state is entangled. The conditional entropy of the channel, if it is less than minus log A, why? Because minus log A is the minimum value of entropy of the channel, right? So in that sense, it is related. Yeah. So if it is less than minus log A, then that implies channel is signaling from A prime to B. And what do we mean by signaling? It means that the input at A prime affects the output at B. Now, conditional entropy being negative is negative for all pure entangled states. The conditional entropy of channel is less than minus log A for all unitary channels signaling from A prime to B prime. If unitary is signaling from A prime to B prime, then it is always less than minus log A. There is a strong subadditivity, which is to say that conditioning does not increase entropy. So the conditional entropy of A given BC is always less than equal to conditional entropy of A given B for all states. That is strong subadditivity result holds. This is also as conditional mutual information of state is always non-negative. Similar result also holds for the channel. The strong subadditivity like result also holds for the channel, for the conditional entropy of the channel. So these are our results. So before this, we take axiomatic approach. We first lay out some of the properties that conditional entropy of channel should satisfy, and then we'll give the formulation and see whether they satisfy these properties or not. Now, since we are talking about conditional entropy, you need to have, for state, you need to have bipartite state. For random variable, you need to have joint probability distribution between two variables, right? So for channel, you need to have bipartite channel. So you can talk about conditioning and non-conditioning systems. So here we are taking A prime and A to be non-conditioning and B prime and B to be conditioning systems. So first property that we ask demand is monotonicity. It should be non-decreasing under the action of local pre-processing and post-processing with unitary channel. So if before the action of channel and after the action of channel, if I apply unitary channels locally on the Alice part, Alice meaning A prime and A part, then the conditional entropy should be non-decreasing. It shouldn't decrease. Second is conditioning should not increase entropy. Third, normalization, that is, if I have trace and replace channel, then I should get conditional entropy of states. And finally, if my channel, bipartite channel can be written as tensor product of two channels, that is two local channels, then the conditional entropy of channel should not depend on the B part. It should only depend on the A. It should be function of just the channel local on A, local channel on A. So these are four properties. Now, how do we derive this formulation? How to get this formulation? So first we see that we define, we don't define, it is already known, like this is way too old. Quantity function, quantum relative entropy, and quantum relative entropy is defined as this function. So relative entropy between rho A and sigma A, this is the quantity which is generalization of KL divergence, which is known in classical information theory. It gives the measure of how far rho A is from sigma A in a sense, okay? And if this condition is not, if the support condition is not satisfied, this value can take infinity, but everything is fine. And for which you can generalize this definition to the channel, with this is again not ours, others have already done this, is relative entropy between two channels or two completely positive maps, is you take something like phase distance and diamond norm. So this is that you assume a reference system and the size of R will be the same as, can be taken to be the same as A. And then you look at the relative entropy of their outputs. Sorry, this would be M. This is not M, this would be M. Okay. And it suffices to optimize over pure input states. It is known that the quantum relative entropy is monotone for states under action of quantum channel, and it is also monotone for channels under action of quantum superchannel. So these properties are known. Using this property, you can show most of the inequalities required in quantum information theory. For example, strong subadditivity, convexity, like a lot of the arguments will follow from this. Okay, and we are going to consider this relative entropy. However, our results also hold if I replace this D with any function that is monotone under action of quantum channels for states. So you can take trace distance, you can take fidelity, you can take max relative entropy, mean relative entropy, anything like generalized Sandwich-Renyi relative entropy. So results also hold for that. For simplicity, I'm sticking here with the von Neumann entropy. Oh yeah, von Neumann entropy. So von Neumann entropy you can get from relative entropy. It is minus sign will be here, and it is relative entropy between rho A with identity operator. And conditional von Neumann entropy can also be telecasted in terms of relative entropy with rho AB compared with identity A and rho B. So please notice here that you always, so for the entropy and conditional entropy, the system A, here we have identity operator. Now, if we are going to the channel, we are going to see, so this is comparing rho A with either maximally mixed state, or you can think a uniform operator, right? Identity operator. And here you have identity A. So what will be the counterpart of identity A for the channel? So this was already done by Gillard Gore and Mark Wilde, so in their work, and also Yuan, around 2018-19. So manual, So consider a replacer channel which is completely positive map, that no matter what the input is, the output is always identity operator. And if you want to consider channel, then this will be completely depolarizing channel where no matter what your input is, output is always maximally mixed state. Okay, so you have that channel. Then the entropy of channel, von Neumann entropy of the channel can be written as relative entropy minus of need relative entropy between the channel and the replacer map. Or if you want to write in terms of this completely depolarizing channel, then you have log A minus relative entropy between M and this completely depolarizing map. And as you see, this can also be written as conditional entropy of output of the channel with respect of output state with respect to the reference state, and you optimize over all possible input to the channel. And this is why the entropy of the channel does not say anything about the channel property in the sense like signaling, like the correlations that channel can generate, because here and its behavior is same as the lower bound was same as the conditional entropy of state, because it can be written as conditional entropy of state even though it is function of the channel. So that motivated us to go beyond this and talk, like to see what will the conditional entropy of channel be. Yeah, so now for the channel, so for the channel we can formulate the conditional entropy can be written as relative entropy of the bipartite channel with respect to completely depolarizing map R and the channel local channel M, and you optimize over all possible channel M. So this is analogous to the definition for state, conditional entropy of this state. You have two definitions possible here. You have two definitions possible, and you can also write this as minus of relative entropy between bipartite channel, concatenation of bipartite channel with replacer map. So these two definition comes, we'll see why we have this two definition. And also we had seen that the conditioning should not increase conditional entropy, right? So if we demand that conditioning should not increase conditional entropy, then should not increase the entropy, then you need to have the notion of reduced channel. So for state you have reduced state, but how do we define marginal? Marginal of the channel is not well defined if you have signaling channels and all. So what we do here is we kind of take a straightforward generalization from state to the channel. We just partial trace the output. So if you partial trace the output and you define reduced channel in this form, then all those four properties are satisfied. And the strong subadditivity like result also follows from here. So if you consider this to be reduced channel, then you get this, and also strong subadditivity like for the channel. So what is the idea behind this? So idea is to channelize this function of state to the function of channel. So here bipartite state is replaced with bipartite channel. Identity tensor, the state is replaced with replacer. Since sigma b, you were optimizing over all possible sigma b, so sigma b is the CPTP is replaced with CPTP map here. Here you don't have freedom over optimize, like over rho b is reduced. Yes, so how do we get identity tensor rho b? You can get identity tensor rho b if you add replacer map on rho AB. So R remains the same and rho AB is replaced with bipartite channel. So if we do this, we get those two definitions. Now in this, yeah. And notice that the second definition, in which you had relative entropy of bipartite channel with respect to this channel here, can be written as conditional entropy of state. Okay. So that is why the first definition is the preferred definition. The first one is preferred definition. We say that at least we call it as more genuine conditional entropy of the bipartite channel, even though this both satisfies all the properties. But this is something that gives something unique about the channel, whereas this does not. However, both are valid definitions. Yeah. So for an arbitrary bipartite quantum channel, we show that the first definition is lower bounds the second definition, and we call this as no signaling conditional entropy, because this doesn't, whether you have signaling channel or no signaling channel, you can still write this as conditional entropy of state, whereas for this you cannot. And if your channel is signaling, then the strict inequality holds. This is always strictly lower bound on this. Whereas if your channel is no signaling, then the equality holds. Okay, for no signaling channel, equality holds. And for telecovariant channel, you can show that the conditional entropy is equal to the conditional entropy of the choice state. So phi n is the choice state minus log a prime. So for swap, you see you will get minus 3 log a. If you have swap channel, swap unitary swap gate, then you will get minus 3 log a here. Because for maximally entangled state, if the choice state is maximally entangled between party A and B, then this will be negative. So you can get lower than this. Okay, so that is it. So yeah, that is it. Thank you.
So fast, that's good. So questions? Anybody having questions?
Yeah.
Sir, as you discussed that the conditional and entropy means there is a correlation between two system or particles. If it is negative, means it is entangled. So it means that the information will transfer more fastly. Is it right or not? Because if system is entangled, if you know the one state and other state can also be determined. So
yes, so there we don't allow for faster than light signaling. So if you measure only you know. So until and unless you communicate with the other party, they don't know what they are, which state they are in. Okay. So and this communication from you to that will require time.
So how?
So you don't violate any signaling criteria.
So how you are applying this theory, the conditional entropy to the qubit or system?
Sorry.
So how we are implementing these things, this theory, to a real life system?
Oh, for QKD, it's like, let's say if you're, there are many ways. I mean, you apply this in thermodynamics, QKD, all this, like lot of ways. So knowing that state is entangled, knowing that your conditional entropy for qubit system is -1, says that you both are correlated and there is no correlation with eavesdropper, right? It is maximally entangled state. So you also use this thing like these entropies and all to calculate how much of secret key can you generate. So these are given by this function.
Okay, thank you.
Okay, so in a way, entanglement for state is mapped to signaling in case of channel, and pure there is mapped to unitary for the channels.
Okay. Any other question? If there are no questions, let's thank Siddharth.
Thank you.
Next speaker is Labha Rai from Bardhaman University. And I think again he is going to talk quantum information theory, many body particle.
Can I have the clicker? Cool. Thanks. Oops. What's going on? Very good. Back. Okay. Sorry for the delay. Hi, folks. My name is Onula Vorai, and today I'm talking about what happened here. There we go. So today I'll be talking about dynamical many-body localization in flow-case spin chains. I'll try to keep it as generic as possible, but I'm still going to predominantly focus on 1D spin chains, although some of the results that I'll be talking about have been generalized to other systems as well. But I'll mainly be focusing on spin chains here. Yeah. So here is an approximate introduction and overview of my talk. So first I'll start by talking about many-body localization. Now, many-body localization, or MBL, this is a phenomenon where isolated quantum states, they don't reach thermal equilibrium. Isolated quantum many-body states, a very high degree of complexity. And they retain memory of their initial states. So this is in contrast to thermal systems where that doesn't happen, where if the system thermalizes, it loses all memory of its initial conditions and all state information very, very quickly. Whereas in MBL systems, the spread is much, much slower. Ideally, it doesn't spread at all. And but in practical reality, it might spread, but if it spreads, it will be here. So I'm going to primarily focus on quantum many-body systems that are being periodically driven in time externally. So these are called flow-case systems, and these periodically driven flow-case systems can exhibit MBL even without disorder, which is usually a requirement for MBL and static systems. I'll discuss that in a minute. Now, when we are driving a system periodically, the periodic switching of the Hamiltonian, this can actually induce energy localization or localization in energy space. So here is a sort of artist's conception of how thermality at infinite temperature, shown here on the right, contrasts with athermality in DMBL, shown on the left, in the energy space, or more specifically in the Floquet-Hilbert space of a many-body system. So this is sort of a percolation diagram, right? It links all those quasi-stationary states that allow for direct transitions between them. So for the thermal case, in thermality, everything is linked to each other, right? So that means, and the entire system grows exponentially with system size. So this allows for the system to traverse the full Hilbert space through transitions, whereas MBL would look something like this, where the quasi-stationaries are all broken into non-overlapping sectors, and these sectors grow very slowly or not at all with system size. So this means that if you populate your system in a state that's a null sector, the dynamics is pretty much going to keep it there. And that's a relatively tiny region of the Hilbert space, and it's not going to move from one sector to another that much, even though the different sectors are energetically linked. The different sectors are energetically accessible to each other. So this will happen because of what are essentially approximate conserved quantities that will appear from the dynamics of the system, rather than from the symmetries of the Hamiltonian. So MBL in periodically driven systems also allows for the formation of certain exotic quantum orders. One such order that I'll be talking about, I'm sure you've heard of it in semi-popular literature at least, is called a time crystal. specifically Floquet type crystals. So these time crystals are special exotic states of matter where time translational symmetry is spontaneously broken, much like spatial translational symmetry is broken in a regular. So it's like a regular crystal, except it's in time rather than in space. So in order to protect these time crystals from melting, you need to induce many-body localization. There's at least one candidate for discrete time crystals. So this makes many-body localization a key area of study in non-equilibrium quantum dynamics and quantum phase transitions. Since time crystals are a potential candidate for fault-tolerant quantum computing, this has relevance in that area as well. So this work is ongoing and has been done through collaborations between myself over there and my PhD student, Mehboob Rahman at Bardhaman, Professor Arnab Dash at ISCS in Kolkata, Dr. Takashi Mori, who was formerly at Riken Institute in Tokyo, and now he's at Keio University in Japan, and Dr. Akitada Sakurai, who's at the Okinawa Institute in Okinawa in Japan. So it's a collaboration between us here. And if any student is interested in participating in our research activities, then we are open for PhD candidates. I have an opening for one PhD candidate. So interested students can contact me. I also have a couple of projects on biomolecular dynamics and so on. If there are students who are interested in that area, they can look me up as well. Okay. Right now, let me just talk about my motivations here. I shan't talk about the fundamentals of ETH and MBL that much, but very briefly, even though pure quantum dynamics is perfectly regular, there's no chaos or anything in there because Schrodinger's equation is linear. Even if that is the case, we expect sufficiently complex quantum many-body systems, particularly non-integrable ones, to exhibit thermal behavior for few-body observables. So the ETH, the eigenstate thermalization hypothesis, makes a proposition. And that proposition is that for most non-integrable systems, if you look at typical energy eigenstates, that is to say, energy eigenstates that are not the ground state or low-lying excitations, because in a closed isolated systems, they have no particular preference. So if we ignore those, or ignore very high energy states that could be edge states or whatever, we ignore all those, then for all the other states, the structure of the eigenstates should themselves contain thermal behavior in them. That's the expectation of the ETH, that the complex many-body structure of the states themselves have like Boltzmann weight-like terms. And if we actually populate a system in a linear superposition of such eigenstates, then eigenstate expectation values of observables are sufficiently smooth functions of energy to reveal thermalization through dephasing dynamics. That is what the proposition is in a nutshell. So Marcus Rigol and Maxim Olshany had a landmark publication in Nature in 2008, and the schematic here is taken from that paper, and it shows this principle schematically for a classical system. In a phase space, the initial state is just one point on a constant energy hypersurface. Over time, nonlinear dynamics and chaos and so on will cause this to fill up the entire hypersurface, and the system can attain ergodicity where time averages can be replaced by ensemble averages. For a quantum system, the situation is a little bit tricky because this type of dynamics can't happen. So for a quantum system, you would see something like this, where the different energy eigenstates themselves contain thermal structure. And any observable A, if it evolves in time, will have a time average that can be easily mapped to a diagonal average, where these C alphas are the components of the initial state in the energy eigenbasis, and A alpha alpha are the diagonal matrix elements with respect to the energy eigenstates. Then once you've averaged out all the off-diagonal components, this is what diagonal average will look like. And if this is sufficiently smooth in energy, you can replace this by a microcanonical average. This is the proposition of the ETH. It's a hypothesis. It's not proven. However, obviously, this hypothesis can be questioned because exact quantum dynamics does preserve the memory of the initial conditions, even though this doesn't. Because whatever is the initial condition, whatever initial condition you have, that's contained in this, and this sum is always 1 for unitary dynamics. So initial condition information is gone at the end. But in exact quantum dynamics does preserve the memory. So exact quantum dynamics should allow for athermalities. This should not be universally true, should allow for athermalities. And there are many interesting athermal many-body phenomena, such as quantum scars and Hilbert space fragmentation and so on. I'll be talking about a slightly more traditional form of athermality, which is many-body localization. This is a phase of matter where the system is essentially nearly static for a long time, in contrast to a thermalized system. So what that means pictorially, I can illustrate this, let's say, for a gas in a box. In a thermal system, if let's say T is equal to 0, all the molecules are prepared, let's say, on one side of the box and then thermalized and let go, then over time this will diffuse out and the molecules will pretty much fill up the entire volume of the gas. If we could somehow engineer many-body localization in this gas and repeat, then in the same time scale, the dynamics will be much, much slower, and the configuration of the atoms will preserve the memory of its initial condition, which you won't see here. Broken ergodicity. So thermalization requires that the different components of the system exchange energy and information very, very quickly. That's necessary for thermalization. So therefore, a thermal system must be very strongly conducting. So if you want to look at athermal behavior, a behavior where ergodicity is broken in a system, then one interesting and natural candidate is to find insulating systems, the systems that show insulating behavior. One such is a non-interacting system with a disordered potential where the system can exhibit something called Anderson localization. So here, in Anderson localization, I've shown it schematically for a one-dimensional spin chain. Here you can see that if the underlying potential is disordered, then a state prepared with spins excited here, the state will not spread much, and this will pretty much stay localized because the disorder basically prevents one subsystem of this system from interacting with other subsystems. So it's localized, and you can't have combinations where one system acts as an equilibrating path for the other. Now, Anderson localization is a single particle phenomenon. Right, so it's a non-interacting phenomenon. If you add strong interactions to the particles or the quasi-particles or whatever, this will bring us to the realm of many-body physics. And if you can see behavior that's similar to Anderson localization there, what you have is many-body localization. So thus, it seems that disorder is important for MBL, which is great, but that presents a technical, conceptual problem, which is that disorder-induced MBL is almost always pre-thermal. What that means is that it doesn't actually arrest thermalization, it only delays it. Now, the reason why this happens is that, I mean, if you consider, and what Anderson localization actually predicts is that the overlap of the Hamiltonian matrix element between different Anderson localized states decreases exponentially with system size. So you might say, yeah, in the thermodynamic limit, it's gone, so there's no mixing. But the problem is that the smallest possible energy gap in a system, in a many-body system, a non-integrable many-body system, is also exponentially decreasing with increased size. Not exponentially, it's 2 to the minus n. It scales as 1 over d, where d is the Hilbert space dimensionality. And if you have like a random, very complicated Hamiltonian of spin half particles, then we expect the dimensionality to be 2 to the n, and the smallest possible energy gap to be 2 to the minus n. And if the overlap between localized states is e to the minus an, well, even in for large n, these two can become comparable. And if they can be comparable, then there could be transitions between these states, even in the thermodynamic limit for very large n. Now, in regular Anderson localization, this doesn't present a problem because that's a non-interacting theory, as I said. And for non-interacting systems, the smallest possible energy gap is typically of the order of 1 over n, which in the limit of large n is huge compared to e to the minus an. So we can ignore it. But in a many-body problem with strong interactions, that doesn't. So look, you can obviously, it's e to the minus an is the overlap. By controlling the decay rate a, you can try and stretch the time in which the system is going to show any dephasing dynamics or any transition dynamics. But no matter how much you stretch it, if you wait long enough, this localized system will delocalize and it will thermalize. So all NBL systems are essentially pre-thermal if they by disorder. So now the goal is to try to find NBL in disorder-free systems. What about them? So in such systems, if we try to induce time periodic dependencies in the Hamiltonian through external means, then time periodic driving can be used together with Floquet engineering to induce localization. Localization through dynamics rather than through any symmetry properties. And that's what I'll talk about. How to use a phenomenon called dynamical freezing to induce localization. Now, the ETH, when I first talked about the ETH, I was talking about time independent systems, but you can adapt the ETH to work with periodically driven systems as well. That it's called the FETH, or the Floquet eigenstate thermalization hypothesis. What the hypothesis predicts is basically that any periodically driven many-body system that thermalizes will do so at infinite temperature. This makes sense because energy conservation works, you have an external drive, so it will pretty much cause all states to mix equally, and then you will have an entropy of like kb log n or whatever, which is characteristic of infinite temperature. However, we will discuss a case, drive parameters can be engineered to suppress this thermalization. So that's basically the concepts in a nutshell. There are, if you wish to know more about these things, then I have two talks here. I recommend them. There's an excellent talk by David Hughes that's up on YouTube, where he discusses many-body localization and its relationship with thermalization. It does it very extensively and very well. You can scan the QR code there, and if you want to learn more about Floquet engineering and time periodic systems, there's a nice talk by Takashi Oka, so up on YouTube. You can look at any one of these. Now, let me now segue into what I mean by dynamical freezing. Now, the paradigmatic model where this dynamical freezing can be described, this is an integrable model, but this is just a paradigmatic instance, an example. So this is a familiar, this is the one-dimensional transverse field Ising model. So you have Ising spins here, these sigma ix that are laid in a one-dimensional chain, and I only consider nearest neighbor exchange between them. All other spins don't interact. And I also apply transverse field that's driving the Z spin. And this transverse field is time periodic. Just as a concrete example, I'm making it harmonic here. So so this model is an integrable model. And so if you simply do a transformation to hard sphere bosons and follow that by a non-local Jordan-Wigner transformation, then move to momentum space, the Hamiltonian can be made to look like this. So this allows to translate the dynamics of magnetization. Magnetization is given by the expectation value of the Z operator here, sigma Z operator here, and this maps to the population dynamics of these spinless fermions here, Ck dagger Ck and C minus K dagger C minus K. And the Hamiltonian can be written as a sum of uncoupled Cooper pair Hamiltonians. If you break these matrices and vectors, you will get ballistic terms where there's a time periodicity, and these off-diagonal terms that correspond to terms like C dagger K, C dagger minus K, which are Cooper pair terms. So these delta Ks and FKs, they depend upon the nature of the J and all, but for this bare model, this Fk is just cosine K and this delta K is just sine K. So each pair is a quantum two-level system, and so this is an integrable system. I've just decomposed it into a sum of an extensive sum of local of quantities. So it's an integrable system. So let's look at what I mean by freezing here. So, sorry, yeah. Now, suppose I'm driving this with a very high frequency, not a low frequency. In general, a driven TLS can't be solved exactly, but there are adiabatic solutions in the low frequency limit. But I'm talking about the opposite, which is the high frequency limit. In the high frequency limit, a time periodically driven quantum two-level system can show a phenomenon known as coherent destruction of tunneling that was reported a long time back in 1991 by Grossman and Hoyingi and a couple of others. The seminal paper is cited up there. So what happens is that for very rapid drive frequencies, you can try to solve this, you can try to simplify this Hamiltonian approximately using analytical techniques. And one such analytical technique is called the RWA, or the rotated wave approximation. So you can apply this as follows. You apply this unitary transformation to the Hamiltonian. So this unitary transformation basically transforms you to the instantaneous rest frame of the driving field. So if the driving field is like a rotation, then this will transform you to the instantaneous rest frame of that rotation. So it's basically just the propagator of this part of the Hamiltonian, not the propagator of the whole Hamiltonian. So there's going to be an omega in the denominator that arises from the integration. And that's this. So for each k, this will happen. And these tau x, tau y, tau z, these are the x, y, z Pauli matrices. I'm using taus rather than sigmas, so because they are different from d spin sigma. These are Pauli matrices here in momentum space. So this matrix, a 2 cross 2 matrix, I can write it as a superposition of Pauli matrices, and that's essentially what I've done here. So if you apply this unitary transformation to this Hamiltonian and do the standard quantum mechanics math, that is, you either use the Jacobi-Unger expansion here, or you use the Baker-Campbell-Hausdorff formula, or whatever. There are many ways to do it. What you can do is you can basically do a Fourier decomposition of the transformed Hamiltonian. This is the Hamiltonian in H prime in the moving frame. And that looks something like this. You can see that this is kind of like the generating function for Bessel functions, right? If you remember your undergraduate mathematical physics. And it's the same basic idea. You apply it here, then all the different Fourier modes are just going to have Bessel functions of the ratio of amplitude and frequency here. So the ratio, so eta, this quantity is twice times the ratio of the amplitude and frequency, and you can write it like this. So this is exact. But now, in the limit that the drive frequency is very large compared to the internal relaxation rates, we may consider what are known as zero photon processes. That is to say, only the slowest oscillating components of the expansion, smoothing out all the other components as too rapidly oscillating. So basically that means that if omega is much, much greater than Fk and delta k, then I can pretty much smooth out all of these oscillations as very, very rapid. That only leaves the terms here that don't oscillate. So that's true for the zeroth mode here. N is equal to 0 here, cosine 0 is 1. This is the only term that remains. These terms remain, and all of these can be ignored. In that limit, the Hamiltonian pretty much looks like this. It's static now. This is the RWA Hamiltonian. But the mixing term is linked through a non-monotonic function of the amplitude and frequency. This is the zeroth order, the zeroth Bessel function. If you plot that here, you'll see that it's got roots. So even at very high frequencies, if you adjust the amplitude such that the ratio lies on any one of these roots, then this guy goes away. And then the Hamiltonian is essentially completely ballistic and therefore is localized. It's approximately localized, of course, because I'm doing an RWA. RWA is not exact, it's an approximation. So it gives you an extensive number of approximately conserved quantities. So the theoretical background, as I had said, you can find that in these papers here. And there's even an experimental realization of this phenomenon in an organic molecule where they actually detected these responses using NMR techniques. That's on the lower paper here. Anyway, so now in our work, which is cited in this paper, which was published in Physical Review B last year, started by trying to quantify the extent to which the TFI, driven TFIM, is frozen or localized. And one way to profile that is by using a quantity called the inverse participation ratio and measure that for the different Floquet modes of this system. So now let me give a quick and brief introduction to what Floquet's theory is. Periodic quantum systems obey Floquet's theorem. So in Floquet's theorem states that for a periodically driven quantum system evolving unitarily, the propagator can be written in this form. It's a product of two propagators. The first subpropagator is called the micromotion. This operator kf as a function of t, this shares the same periodicity as the Hamiltonian. And you can adjust your reference frame in such a way that at t is equal to 0. So that means if you strobe the system at integer multiples of time of the time period, this doesn't matter. And if your frequency is very, very, that doing this discrete strobing is not fundamentally, not quantitatively very different from looking at the continuum, then in that limit, your propagator just has this term left. And this is a time independent dynamic. So HF is what is called the Floquet Hamiltonian. It's a different Hamiltonian from the Baire Hamiltonian, but it maps to the Baire Hamiltonian. And this is an effective time independent Hamiltonian, which at least at integer multiples of the time period reproduces the dynamics of the time dependent Hamiltonian. And the eigenstates of this HF, they are known as Floquet modes, and the eigenvalues are known as quasi-energies. So one way to quantify localization in periodically driven systems is to look at the inverse participation ratio of these Floquet modes. So the Floquet modes IPR, or inverse participation ratio, shows how localized these quasi-stationary states are. Now, thermal systems have equal participation in all physically relevant basis states at infinite temperature. So the IPR should be relatively small. Ideally, the IPR should scale inversely with the Hilbert space dimensionality. So if the IPR varies, time's over? Oh, okay. So, okay, if the IPR is much more than that, then it's localized. And ideally, if the IPR is 1, it's completely localized. So the IPR is often computed as the square of the integral of the square of the density. In each case, we choose a physically meaningful representation. Here, that would be the momentum. And look at the reduced IPR for a particular Floquet, many-body Floquet state. And look something like this. Here I have the momentum of the Brillouin zone. Here I have 2h over omega. I'm running a simulation here for about 100 spins. I'm setting the omega to a very high value so that it's very rapidly oscillating. So in our dimensionless units, that's about 90. And I can see that when 2h over omega lies on these dashed lines, which are the roots of the Bessel function, the IPR is essentially 1 for all the momenta. As you start to move away, the IPR reduces. But of course, the IPR never reaches 1 over d. The reason is that this is an integrable system. So now we generalize this to a non-integrable system that is already known to thermalize at low frequencies. So this is known as the Lipkin-Meshkov-Glick model. The seminal paper for that is here. And it's a long-range model. It's the same Ising model, except now, instead of nearest neighbors, all pairs of spins interact with each other. So it doesn't matter what the dimensionality is or what boundary conditions are. Everything else is the same. For here, if you, okay, I'll skip some of the details here because the propagator looks like this, is the same propagator from before. If I now transform to H tilde, just like I did for the TFIM, and do the same RW, I essentially get what is practically the same result. It just looks a little bit different. I've still got a J naught of eta here. If I adjust my, here my Floquet parameters, drive and frequency and amplitude parameters such that J naught of eta is 0, that goes away. And because of the fact that this system preserves the total spin, I can, yeah, sorry. Yeah, then if this term goes away, then you only have this term if the total spin is conserved. So this is a constant. And so it's proportional to Sx square. And you again have an extensive number, approximately conserved quantities, and the system will be localized. So again, we have some numerical results here. This is again the IPR, except here instead of momentum, what I have is I populate the system in the totally symmetric subspace where the total angular momentum is the largest value. And so this is basically just a quantum number in the S square Sx dual representation, just like you do in regular quantum mechanics of angular momentum. And over here, I have 4h over omega. This 4 is not 2 because of some technical scaling in this Hamiltonian. But anyway, the underlying structure is similar. At the roots of the Bessel function, the IPR is 1. If you move away, the IPR drops down to nearly 0, which is what is characteristic for thermalization. That doesn't happen in the TFIM. It at most drops to 0.5. And you can see here, for low frequencies, the IPR is nearly 0. In fact, it scales in the asymptotic limit as 1 over n, which is what you expect for a thermalized system. This is consistent with the low frequency thermalization that has been reported for this model in the literature. Here is a cited source for that. But at higher frequencies, it undergoes, if you increase the frequency and the amplitude such that it's always on the root of the Bessel function. At low frequencies, the RWA breaks down, so that's everything that I described doesn't work. It thermalizes, but as you increase the frequency, it undergoes an analytic crossover, and the IPR goes to unity. So this allows for a phase crossover from thermal to local and back. So the next thing that we did is apply this to our time crystal so that we could achieve a time crystal without disorder. So in the interests of time, I'll just report that our result has been published in the New Journal of Physics last year. And so the idea behind this is that if I have a spin chain, I basically use a square wave to flip between two Hamiltonians. So in the first half of the square wave is just a static field, and the static field's amplitude has been adjusted in such a way that half the time period, all the spins flip. Then in the second half, I have a time periodically driven spin chain that's engineered to be at many body localization. So what happens is that the first half, the spin flips, then it stays localized, then this Hamiltonian switches back on. This allows the spins to flip back, flip, localized, flip, localized, flip, localized, flip, localized. So what is that if you strobe the system at integer multiples of the time period, your Hamiltonian appears to be static. But since this has a period of 2t rather than t, the state appears to be time dependent, thus spontaneously breaking discrete time translational symmetry. So then, of course, the thing is that here we used a more general Hamiltonian in our numerics, where we had continuously varying ranges rather than just both nearest neighbor and long range. What we saw was, and this is, I guess, my final result, is that we need this localization in order to protect this time crystal from rotation errors. So if there are any rotation errors, if there are any tiny variations ordering field in the first half of the square wave, that will cause the time crystal to melt. But if we have a localization in here, that melting will be very, very slow. It will try to prevent the melting from happening. And what we've also seen, something that's very interesting, is that if you have different zones with different localization errors in them, then in regions with small localization error, you wind up with a discrete time crystal shown here for the regional magnetization. It eventually melts because of rotation errors, but the melting is very, very slow. And on the regions with high rotation error, you have a continuously localized system. So you have a spatial separation between synchronized and asynchronized oscillations, and this is similar. This is a quantum version of what's known as a chimera state, or a chimera-like state. Chimeras have been reported in nonlinear classical oscillators, and they're a very interesting topic in nonlinear dynamics, but nobody had ever seen a quantum chimera before, and we've, I think, come very close to reporting what is essentially a quantum chimera here. But other than that, and we've also seen that, okay, here I can skip all this. Finite size scaling is definitely works. It's characteristic of time crystals. So the fact that this is a time crystal is well known. And we've also profiled it for different types of rotation errors in different regions and so on. But anyway, I mean, suffice it to say that we've reported the successful modeling of a time crystal. And yeah. So this is a summary of our research work. And as an outlook, what we're trying to do now is we're trying to see if we can use this dynamical many-body localization to create highly efficient MBL engines. So there's some work by Nicole Junger-Halpern, who's been looking at the possibility of basically preparing a state in a preparing a system in a thermal state, and then adiabatically varying it to a localized state and then bringing it back to a thermal state. So this would correspond to a thermodynamic cycle, and to look at the efficiency of this cycle. And it turns out that the work statistics of these cycles are highly efficient. So they're very close to Carnot efficiency. And our goal is to see if we can replicate that in dynamically many-body localized systems, which will be more stable than disordered MBL systems. And we're also looking at other ways to localize dynamics in discrete time crystals. One candidate is a Floquet flat band. So these are basically, the idea is that if you have more than one square wave switching between different Hamiltonians, you can have the square waves switch in syncope like this, in such a way that after exactly one time period, the propagator is unity. And what that means is that if you diagonalize it, the bands are all flat. The quasi-energies have no dependence on any degrees of freedom. These are flat bands, and they have no group velocity, so they will never, so any state populated in them will never thermalize, they'll be localized. So this is something that we're working on right now. So I guess that's it. That's my talk. Again, these are my collaborators, and I've received funding from ANRF from this core research grant, and I've also received some funding from the University Grants Commission, which is this BSR startup grant. So these are my funding sources. Sorry, I stretched it maybe a little bit longer than I should have.
Right. Yeah. So any questions?
What should be the analog of Brillouin in the time crystal?
An analog of the Brillouin zone in the time crystal. Well, I guess that would be the percolation diagram of all the Floquet quasi-energies. So two Floquet quasi-energies will be linked if the difference between their quasi-energy value is less than a certain integer number of multiples of the drive frequency. That would be the analog of the Brillouin. Because the conjugate of position is momentum, and the conjugate of time is energy. So since this is in time, the conjugate would be energy, and the stationary states would be the quasi-energy states. So that would be the analog of the Brillouin. Yeah.
You didn't talk about the scars.
Sorry?
Scars, you didn't talk about that. Scars.
Oh no, I didn't talk about other forms of athermality like scars. An interesting candidate that a lot of people are looking at now are his Hilbert space fragmentation, which has some similarities with many body localization, but there a lot of the invariant subspaces are like completely rigid, and they don't scale with system size at all. Here it does, but it scales linearly with system size. It's sub. There it's nothing. So.
If you take the Floquet system, if you want to use it for the engines and all that, the issue is that because you have the external driving, one should also take into account the energetic cost for the external driving.
Yeah, we will. We're going to do that. So, I mean, what we're simply going to do is that we have an external drive, and when we look at the work statistics, then I mean, we're going to look at the full density matrix. So it will be something like whatever. If we are varying the drive parameters adiabatically in time, so it will be the integral of the trace of rho dh dt, where rho is the density matrix. That's going to contain system and external and everything. So yeah, we're going to have to do that. Correct.
You said that the formation of time crystals is because of the spontaneous breaking of the time translation symmetry.
Discrete time translation. Discrete. Continuous time translation symmetries are tricky. They can't be broken and so on.
Okay, could you explain again like how this happens?
The idea of the time crystal was originally proposed by Frank Wilczek in 2012, where his basic argument was that, hey, if spatial symmetry can be spontaneously broken, why not time translation symmetry? But as it turns out, if you do the math a little bit, there are some issues with Elitzur's theorem in gauge theory that for which time crystals don't really work out well in equilibrium and don't really work out well for continuous systems. So for discrete systems, however, you can break time translation symmetry like this. Suppose you have a system that's time periodic. If you strobe the system at integer multiples of the time period, your Hamiltonian appears to be static, right? Now, suppose you look at the underlying Floquet states. These Floquet states are time dependent, but the Floquet modes themselves are also time periodic. So, if you, for instance, have two Floquet states that are highly degenerate and are linked in the percolation diagram, then what you will have is in the first half, it will transition from one Floquet state to the other, and the second half, it will come back. So the time period will be 2t rather than t. So if you're strobing the system at integer multiples of time period, it won't appear to be static. It'll appear to be changing with time. So if in your universe, Hamiltonian appears to be static, but your underlying quasi-stationary state isn't stationary, then time translational symmetry is spontaneously broken. In my example, it's Z2 symmetry because it's only two Floquet states that are linked. If you could link three Floquet states, it would be Z3. Four Floquet states, it would be Z4, and so on and so forth. And people have actually modeled these in noisy intermediate scale quantum processors over the last couple of years. There's a lot of literature on this. You can Google around and check.
Thank you.
I think we will stop here because the online speaker is there already. We are late by 20 minutes. So we can connect the next speaker.
Hello, can you hear me?
Yeah, we can see you and hear you as well. Thank you for being online. Sorry for being late. We are late by 15-20 minutes.
Okay.
So, pleasure to introduce Marcus Muller from Institute of Quantum Optics and Quantum Information. And he works in foundations of physics and addresses foundations of questions, fundamental questions in physics through quantum information theory. So let's hear Marcus, what he's going to talk about space-time. Yeah.
Great. Thank you very much for the introduction, for the invitation, in particular to Professors Pati and Agrawal. It's a pity I cannot be there in person. I'm not traveling much because of my little kids at the moment, but this will change, and so there will hopefully be another occasion to meet up in person. Let me share my slides. So try that first now. So you should probably see a beach at the moment. And now I'll start my slides. Let's see if that works. Can you see the first slide?
No, actually.
Oops. No. Let's see. How do we do that? So this one. Okay.
Yeah, it's now visible. Now it's visible.
Okay. And now you see it as you should?
Yes. Yeah.
Maximized. Okay, great. Thank you very much. All right. So today I will talk about something about the relation between space and time and quantum probabilities, which is indirectly motivated a bit by quantum gravity, as we had by Jonathan Oppenheim before, but not really about quantum gravity. It's named from fundamental insights to protocols. It's more about the fundamental insights, not about any practical protocols. So the protocols really be just very fundamental and principal ones to illustrate what we found fundamentally here. Here's an outline of the talk. So I will begin with a bit of motivation because the main idea goes back to other people like Wouters and von Weizsäcker, for example. Then I will define what I call rotation boxes, which is a bit like non-local boxes with some inputs and outputs, and do this within and beyond quantum theory. And we can then use this to study how quantum theory is optimal or not optimal in certain metrological games. If time permits, I will also say something or show you how these results can be used to build a theory-independent, semi-device independent randomness generator that builds on space-time or rotational symmetries, and then I will conclude. Okay, so what's the motivation? So here's a very curious observation that has puzzled many people before, which has to do with the qubit Bloch ball and the spatial rotations. So the quantum bit, as we all know, is parametrized by the three-dimensional Bloch ball, and the possible quantum states, the 2x2 density matrices, are in one-to-one correspondence to the vectors with norm less than or equal to 1. So group theoretically, we can see that on the one hand, we have a representation, we have the unitary group acting on the density matrices, but this turns out to be in one-to-one correspondence to the rotation group in 3 dimensions acting on the Bloch vectors. And this is just the insight that the spatial rotations in particular have a faithful representation on a 2-dimensional Hilbert space as a spin 1/2 system. And operationally, you could, for example, say that if you have something like a Stern-Gerlach device that acts on spin 1/2 particles, that you can compensate spatial rotations of your magnetic field with internal rotations of your Bloch vector. So this is a quite curious relation between space and, if you want, abstract quantum probabilities. This has been realized by other people before. It's quite interesting case is Carl Friedrich von Weizsäcker, a physicist and philosopher from Germany. His work is followed now by Holger Lyre, for example, a philosopher in Germany. And von Weizsäcker, before anybody talked about qubits, he has introduced something called the UR, or the UR alternative. And that's a binary alternative. It's the qubit, yeah, out of which the state space of quantum theory can be built. So he realized that you can build everything out of qubits if you have enough of them in some sense. And this motivated him now to say, well, maybe we can actually understand space as a consequence of that. Because UR has symmetry group SU2. If the world is built of URs, then maybe we should expect it to have the same symmetries, and this gives us something like rotational symmetry. Now, this was not seen as something as successful, really, so it's kind of a niche thing, but I think very interesting that what Weizsäcker came up with qubits in the 50s already. Later on, Bill Wouters worked on similar ideas. So most of you will know Bill Wouters, who is one of the pioneers of quantum information theory, introduced the no-cloning theorem, so co-authoring that, and the Page-Wouters mechanism, among many other things. In his PhD thesis from 1980, he looked at the relation between spatial rotations and the state space of quantum theory. And he looked at a thought experiment where you send particles on a polarizer. You look at post-selected states, psi, that depend on the polarizer angle theta. And then you can say, well, so in quantum mechanics, in some sense, the distinguishability of the different states, psi, theta, really have to do with the difference of the angles. And if you look at this and you don't assume quantum theory, then you realize that just to claim this as a postulate gives you that the probability to obtain a click according to a certain angle should be related to the cosine squared of something, some factor n times the difference of angles or so. And this distinguishability here is defined in this way. I don't want to go into the details for time reasons, but he realized that quantum theory is special in the sense that there seems to be a close relation between some spatial rotations and the rotations in the quantum state space and the operational meaning. What I'm talking today is similarly motivated. So this is one thing we do in our group is to try to study this fundamental interplay between, let's say, space and time and probabilities. So a fundamental question to ask is the following. So does the structure of space-time constrain the structure of our world's probabilistic theory? So does it imply some of the structure of quantum theory? In other words, if we know that detector clicks in our world fit into space and time in the obvious way, does this constrain the correlations that we can have, perhaps to those of quantum theory or something similar? Earlier, we worked on how relativity of simultaneity can imply the Bloch ball dimension, that it must be 1, 2, 3, or 5, actually. Also, the quantum 2-to-2 Bell correlations can be understood from something like local rotational symmetry. But today, I want to talk about a sort of systematic mathematical study of the kind of rotational correlations that you can have in prepare and measure scenarios if you assume quantum theory or if you don't, more generally. So we do this, we formalize this with the idea of rotation boxes. A bit like non-local boxes, but they're local actually. But what we could have in mind is a scenario like this. You have a prepare and measure scenario. Your preparation device spits out a quantum system, perhaps a particle, and the measurement device performs some measurement and gives you an outcome. For us in this talk, it will just always be +1 or -1. So we look at 2 outcome measurements. Now the setting or the input to this scenario is a spatial rotation of your preparation box. So you say, my input is an angle alpha by which I rotate the preparation device. And now this gives you a probability of outcome B given setting alpha. This is really very, very simple now. So that's what I just said. Now the thing is, when you look at this more formally, what this entails, then you can say, well, I can think of ensembles of these boxes or these preparation devices, and I can probabilistically, for example, choose one such scenario or another one. This gives me some way to talk about states, all the possible preparations and their mixtures. And when I have these states, and we assume that there is rotational covariance, then we can just use the standard arguments from the textbooks that you should have a representation of your spatial rotations on the state space. We're only talking about rotations along a single axis, right? So not a 3-dimensional, but effectively a 2-dimensional one, which is characterized by an angle alpha. So you expect that your probabilities can always be understood as a consequence of preparing a state omega then performing a transformation T alpha, which represents the rotation group. And then you have a kind of effect or like a measurement outcome EB. Yeah, so this is a bit this kind of general probabilistic framework that generalizes quantum theory. We say probabilities, you pair preparations with measurements to get probabilities. Now, what does this entail? So it says that in particular, if your state space, your space of possible states is finite dimensional, there are not so many representations of SO2. Yeah. In particular, it implies that your probabilities must be sines and cosines. Yeah? So it must be trigonometric polynomials of this form here. You find some integer j, which can be 0, 1/2, 1, and so on, which we may call the spin of the system. And then your probability P of B given alpha must have the form that I've written down here. It must be essentially be a trigonometric polynomial of degree 2j. Yeah, and indeed, whenever we write down a probability or law like this, we show in our paper that, so if it's valid probabilities between 0 and 1 and the sum to 1, that we can think of a state space, some probabilistic system that gives these probabilities under rotational covariance. So what we then define as the rotation boxes, according to spin J, is just the set of all these probability rules. Where you have a probability of +1 given alpha and a probability of -1 given alpha. Well, since they sum up to 1, you only need to specify one of them. Say probability +1 given alpha. Where the probability is really just of that form here. So it's a probability valued trigonometric polynomial of degree 2j or less. Why do we have that thing? Well, you can see that this is just the probability rule that comes from any kind of state space. We have a representation of SO2 that contains these block matrices here. We have a factor of 2j at most in the sine and cosine blocks. Now, I call this a rotation box, so you have different ways to visualize that. What I gave you is the picture at the bottom, a prepare and measure scenario where you rotate your preparation device. But you can also think of that in terms of this kind of left top way, like we have just a single box. Your input is an angle, theta or alpha. Your outcome is plus or minus 1, which you might call A or B. Now, what about quantum theory? In quantum theory, maybe even more familiar and clearer what I'm talking about. In quantum theory, we'd say we have a finite dimensional Hilbert space. On the space, we have a projective representation of the rotation group SO2. And then when every such representation can be written in this kind of block diagonal form, you diagonalize it, has these complex exponentials on the diagonal, and the factor is between -j and +j. Yeah. But the Hilbert space dimension a priori can be as large as you want. Yeah, you have many of these blocks, perhaps. And so we define the quantum spin J correlations or spin J boxes, just those probability rules that come from the Born rule. Yeah. So we say our setup here, our preparation is a quantum state rho. Then when I rotate the box, it acts by unitary conjugation, U alpha rho, U alpha dagger. And then the measurement is characterized by a POVM element E. So all the probability rules that can be obtained in that way are called quantum spin J correlations. Turns out that these sets of correlations are convex. Certainly you can mix them and it's still a quantum one. They are also compact and they are a subset of these more general ones that I've shown you. So the quantum boxes Qj live inside the general rotation boxes Rj. They are a subset of those. What does it mean? It means that every probability rule that you get from this Born rule is actually a bunch of sines and cosines, a trigonometric polynomial of degree 2j or less. Yeah. You can also prove that result. So instead of going through that in all detail, let me just say that you can, if you want, represent every such quantum correlation on the Hilberts on a 2j plus 1 dimensional Hilbert space, as you would expect if you think of a spin J irreducible representation or particle. And actually by preparing a pure state, this is always possible. Yeah. It's not too difficult to show, but it has very powerful consequences. Right. So many ways in which you might think of a system of spin J correlation, they turn out all to be equivalent and correspond to our definition of Qj. Now, how do these compare, the quantum and the more general case? So here are the quantum boxes again. So the probabilities are given by the Born rule with some representation. The general ones are just arbitrary trigonometric polynomials of this the corresponding degree. And clearly the quantum ones are a subset of the rotation correlations. For the most boring case is spin 0. So J equal to 0 means essentially that your system doesn't respond at all to the rotations. So the probabilities are constant. That's what it means. So this is just a set of all constant probability rules where you're independent of alpha. And that's the same quantumly and more generally, obviously. So then Q0 is the same as R0 in this terminology. How about spin 1/2? Well, what we've seen before is somehow the qubit is like really tailor-made, right, to represent spin 1/2 correlation somehow. And this is represented here mathematically by the fact that Q1/2, the quantum spin 1/2 correlation, is the same as the general spin 1/2 correlations, R1/2. And if you depict the set of correlations here, what you can do by just plotting these coefficients, C0, C1, C2, of this trigonometric polynomial, you get a picture like this. So the point on the left of this blue set is just the all zero function. The probability is constant 0. The point on the right is a probability constant 1 function. And the circle in the middle is something like cosine of alpha minus phi. Yeah, so just the usual cosine shifted. And all other correlations are mixtures of those. And you can see what you can see is some shadow of the qubit or of the rebit inside of the set of correlations, which emphasizes a strong correlation between rotations and quantum theory that I talked about, but in a very simple way. What about the spin 1 correlations? Let's see what this would look like. You have a probability rule that looks like this. It's a trigonometric polynomial of degree 2. Yeah, it must be between 0 and 1. So you have these 5 coefficients here that characterize your correlation. Now what you can do is you can go ahead and try to understand the set. And one way to do it is say it's a convex set. So let's look at the extremal points, essentially the pure states of that. Now every extremal correlation must attain probability 0 somewhere. So you can shift them, and you can shift them always so that it attains the 0 at the value 0, at the angle 0. Then you can say, well, whatever that convex set is, the set R1, it's 5-dimensional because it has 5 parameters. I can look at those where it has probability 0 at angle 0. This is also a minimum. You cannot have negative probabilities. You get another equation. The derivative must also be 0. And this turn gives you then a 3-dimensional set of correlations, which turns out to be a phase of this convex set. And it's the one depicted here. It's the spin 1 correlations that attain the value 0 at 0. And what we did was we understood exactly what that set is. We characterized it. We say, what are the extremal points of this set? So the all 0 function, for example, or P1 of alpha, where it's just the sine square of alpha is one of the extremal points. And the other ones are listed here, right? And you can see them kind of plotted in color in this picture. And our main mathematical tool to find these extremal points is called the Fegeri's theorem, which tells that every non-negative trigonometric polynomial is the square, absolute square of some other trigonometric polynomial, essentially. Right? Now, it turns out that all of these have a quantum realization on a spin 1 system. So you can construct spin 1 quantum realizations of all of them, which proves, again, that Q1 equals R1. So for spin 1, also quantum theory is optimal in some sense in allowing all the correlations to be realized. Good. What about spin 3/2 and higher? We get to that soon. But let me first now go to the next part and talk about a more operational reading of this as in terms of a metrological game. So here's a metrological game that Alice may want to play that can fail or succeed with a certain probability. So what's the game? So Alice begins with some spin J system that she wants, whatever probabilistic theory she has at her hands, maybe quantum theory. And then she gives that quantum state or more general system to Bob. What is Bob doing? Bob rotates the system, the preparation device associated to the system, by some unknown angle theta. Now, this angle theta is not chosen uniformly at random, but it's chosen according to this probability distribution function here. Looks a bit weird, but why not? The absolute value of cosine 2 theta plus sine 3 theta, whatever. So this is the distribution function. And then Bob hands the system back to Alice. And then Alice's task is to decide whether, not to estimate theta, but to have a yes-no question answered, namely to answer whether theta is within the gray set of angles or the white set of angles, yeah? Maybe not the most natural game that you might want to play, but it's interesting to illustrate something here about quantum theory. Yeah. Now, what have we now learned from what I told you previously? We've learned everything you can do with spin 0, 1/2, and 1, you can also do with quantum theory. So spin 0, 1/2, and 1, quantum systems are optimal for winning this game and all other games of that form. Yeah. But for spin 3/2, it turns out that the maximal quantum winning probability is 85%. So this is better than random guessing. So random guessing would mean you have actually probability 1/2 for both of these events. But when Alice uses a quantum system, she can get up to 85% winning probability. Whereas some of these rotation box systems allow her to win the game with 88% probability. So in some sense, quantum theory starts becoming suboptimal in this sort of metrological game. So you can think of this as one of the many information theoretic games that people have come up with, but it has an interpretation in terms of space and time here. It's a metrological game, which is a certain variant of an information theoretic game. Why is that? Well, it's because it turns out that the quantum spin 3/2 correlations are a strict subset of the rotational correlations, the more general ones. So these are correlations that have this form here. Yeah. So you have now 1, 2, 7 coefficients that characterize a correlation from the set. And what we've shown in our paper is this theorem here. So if a probability rule has a quantum spin 3/2 realization, then you have this inequality. So you pick these two coefficients, C2 from this equation and S3. It turns out that the sum is less than or equal to 1/√3, which is a tight inequality, which is a bit like a quantum Cyril bound, but for rotational correlations. But then you can write down a trigonometric polynomial of this degree that's always between 0 and 1. So that would represent an alternative hypothetical physical system that responds to rotations in the spin 3/2 way. But the C2 plus S3 is 0.6, so it's larger. So if you draw this kind of set of these coefficients you can have, then the quantum set is a strict subset of the more general one. Okay. Good. So a similar gap can then be demonstrated for all spins like 2 or higher, for example. Good. Now, another insight that we have is, and that's perhaps I have enough time actually to talk about this, is that this can be used for a protocol where the security of the random bits that we generate does not depend on the validity of quantum theory, at least in principle. This is highly non-practical, but let's look at it. So the main motivation here is this field called semi-device independent quantum information, where one of the goals that people have is, for example, to allow the generation of certified random bits. Now you may certainly ask, why don't we just send photons on a half-silvered mirror or so, right? Now this is for the ones among you who haven't seen this before. But then the answer is, well, you may not trust your devices. Maybe you have an eavesdropper, and the eavesdropper knows a lot more about your setup than you do. So the eavesdropper may know, for example, a bunch of variables lambda that you have no idea about. All you see is the mixture over the lambdas, whereas the eavesdropper knows the lambda actually. And so the eavesdropper may be able to predict the outcome even if it looks unpredictable to you. The gold standard to prevent this is known as device-independent randomness expansion, for example, where you have a space-like separated scenario with two parties, and you have a violation of a Bell inequality, which certifies that the outcomes, in some sense, that you find under some conditions are uncorrelated with the rest of the world, and no eavesdropper can predict them under no signaling assumptions. So here's a talk by Antonio Athene, where it explains this for those who haven't seen this before. But the point is that this is quite impractical, right? And you might want to do something more practical, which is called semi-device independent scheme, where you do allow some communication between the parties. You don't have to have a sort of loophole-free Bell test or so, but then you have to add an assumption that guarantees your security. And what people have done, for example, in many works in the past was to say, well, I know nothing about my devices, but I believe that the system that's sent from preparation to measurement is a qubit. So it has Hilbert space dimension 2 and not more. Yeah. And now this allows you to conclude, for example, if you see a certain set of observed correlations in your statistics, that the data is essentially, or to some extent, uncorrelated with the eavesdropper. So even if the eavesdropper holds this additional variable lambda, the conditional entropy that quantifies the uncertainty of your outcome, given the other variables, your inputs, and the eavesdropper's knowledge is still positive. Okay. There's certainly a drawback to this, and this assumption that you send a qubit is perhaps not the most physically well-motivated one. Yeah. It's you can have side channels that you don't know about, and then you don't know whether the eavesdropper might actually predict your outcome. Also, the settings, in many cases in experiments, these settings are not really abstract labels, but they are indeed spatiotemporal quantities. So perhaps you're actually rotating a polarizer or so to do your preparation. And now this is certainly taken care of in our formalism. So the idea is now that we use the formalism for rotation boxes. Replace the dimension bound by a sort of spin bound. We say the system is not a system of type of a certain Hilbert space dimension, but a physical system of a certain type of response to spatial rotations, which is, I think, slightly more physical, which does not assume the validity of quantum theory. It may not be the most practical thing to assume, but it will, I think, illustrate some of the foundational insights that we want to have here. So let's see. The way we can do this is by saying that we, instead of allowing arbitrary angles between 0 and 2 pi, we just have two choices. Say angle 0, where we don't do any rotation of the preparation device, or angle alpha, like 30 degrees or so, something fixed, and fixed angle alpha. Now this now gives you two possible probabilities that characterize your correlation. So you say the input is either 1 or 2. If the input is 1, I look at the angle 0. If the input is 2, I look at the fixed angle alpha, like 30 degrees or so. And then I have these two probability that characterize my correlation. Correlation, sometimes it's better to have, instead of probabilities between 0 and 1, you say how correlated to anti-correlated is the outcome, which is something between -1 and +1. And so you can now define, in this scenario, if you have just two settings, what are your quantum and your more general rotational correlations that you can have? And this is what I called here QJ alpha and RJ alpha. Yeah. You look at these correlations above for these two angles only two settings that are possible under the assumption of quantum theory or not. Now, a priori, we might think these should be different because for spin 3 halves and higher, we know that if we look at all possible angles, there is indeed a difference between the quantum and rotation set. But turns out this is not the case for two settings. For two settings, they all agree. So you can understand the set of quantum correlations exactly just as a consequence of rotational covariance if you want. Yeah. Indeed, you can characterize this explicitly by an inequality. So on the bottom here, you see the square roots, yeah, and the E1 and E2 are these two correlations that you measure, and they must be larger than or equal to essentially cosine of J alpha. A priori, you might see this and say, well, these are like square roots of probabilities. That smells a bit like a quantum amplitude. That seems characteristically quantum, but it's not. Yeah, it follows directly just from rotational covariance without assuming quantum theory. And in the picture, you see this kind of blue set is the kind of set of correlations that you can get. So you have E1 and E2 are the two parameters characterizing your correlation, and what you can get is this sort of blue set, which depends on J and on your angle alpha. So indeed, your correlations here are perfectly characterized by rotational symmetry, where you don't even have to assume quantum theory. Now, you can use that here if you want to get a sort of theory-independent, semi-device independent randomness generator, which only relies on rotational covariance. We say the following. I have an input to my preparation device. If it's 1, then I do nothing to the preparation device. But if the input is 2, I rotate it by some fixed angle alpha. Yeah. And now we need an assumption. Since we're in a semi-device independent regime, we need to assume something about the physical system that mediates between the preparation measurement device, which is now not a bound on the dimension of the system, but are bound on sort of the sensitivity that it has to rotations. And that's what our parameter J says. So we say that the quote unquote spin that we have here for a system should be upper bounded by J. We're not making any further assumptions on the devices or the systems, and we do not assume the validity of quantum theory now. And what you can now do is the following. You can say, okay, what can the eavesdropper know in this case? And let me just through that quickly because time is running out. But the classical correlations that can be predicted perfectly are sort of those in the corner. So -1, +1, +1 means that the outcome is really independent of your setting, and the eavesdropper can always predict this. There are also interesting deterministic relations where the outcome is a function of your setting, right? And maybe you observe a correlation that looks random to you and non-deterministic, but it's actually a mixture of these deterministic correlations. And the eavesdropper knows the additional variables lambda that generates this mixture, and so the eavesdropper could perfectly predict what's going on. In this case, the eavesdropper could predict your outcome, but since we have only these correlations here possible for some choices of J and alpha, this means that the deterministic interesting correlations cannot be attained if we make our semi-device independent spin assumption. And this means that even an eavesdropper with additional information cannot predict the outcome. So the sort of interesting deterministic correlations are then forbidden by our assumptions. And the only ones that can be perfectly predicted are the ones on the red diagonal, like the boring ones and their mixtures, right? So as soon as we observe a correlation outside of the set, we can certify some randomness against the potential eavesdropper with additional classical side information. And this fact, and also the amount of random bits that you could certify in this scenario, is then independent of the validity of quantum theory and of the probabilistic theory that describes your physics, as long as you're kind of justified to assume a bound on the type of system of spin J and rotational covariance. All right. So just to summarize, I maybe go through it quickly. I motivated this kind of foundational study. We started the rotation boxes for spin J, found agreement for spin 0, 1, half, and 1, optimality of quantum theory. By the way, these turn out to be the spins of the fundamental particles that we've determined so far. But interestingly, for spin 3 halves and higher, quantum theory is not optimal anymore. We've seen application in metrological gains, and this allowed us to characterize, for example, for two settings only the correlations exactly, and they turn out to be determined exactly by covariance, no matter what the spin J is. So I want to thank finally my collaborators here, Caroline, Stefan, Thomas, and Albert, who co-authored this paper here that has just appeared, well, a couple of months ago in Communications in Mathematical Physics. There's also another paper on the randomness generation, which is under review right now. Okay, thank you very much.
Thank you, Marcus. There are questions? If there are questions, yeah.
So my question is that, does probability depends on past and future?
Sorry, does it depend on?
Past and future.
I didn't understand that again. Very sorry. The sound is not the best. Can somebody put it perhaps in the chat, or can you spell it?
He is asking, does probability depend on past and future? Past and future, whether probability depends on that. That's the question he's asking the student.
The probability depends on past and future. So I think in this prepare and measure scenarios that we have here, we really just say, so first we assume that we can sort of repeat the setup many times and collect statistics. We have a sort of an IID assumption in the background. And then we would say the probability really only depends on the setting of your preparation device, which means, for example, that the measurement device is a priori uncorrelated with all further past events in your past light cone. There shouldn't be pre-shared entanglement, for example, between preparation and measurement device. However, you can show that you can have shared randomness between preparation and measurement device, and this doesn't change the results. But you shouldn't have shared entanglement, for example. That's like
there is another question.
I just wanted to ask, You considered rotation and SU2 and SO3 kind of a homomorphism. Similar homomorphism exists between SL2C and SO31. So, and say, suppose I take Stokes parameters, polarization. So they transform under SL2C, and Lorentz transformation will also come into picture. So do you think that will have a generalization of this kind of a probability picture?
Yes, so I should say that what we do here, this mathematical work, is sort of agnostic. It doesn't assume or make any like assumptions that there is sort of a fundamental relation of the one that von Weizsäcker predicted or assumed. We're not saying space emerges from quantum theory, though that's perhaps an idea in the background. We're just saying, suppose I have a symmetry group acting on my preparations, whatever that means. Yeah. Even the rotations here could be spatial rotations, or they could correspond to some periodic time evolution, perhaps in quantum theory, or have some other meaning. And so the Lorentz group, or SO3, as you described it, they could also mean many different things. It could be a space-time transformation in the usual sense. It could be an internal transformation of your state space. And all we really did was just map out how the possible correlations can depend on a group element. And the meaning of the group element is not really assumed here, right? Certainly the kind of most colorful and immediate interpretation of what we do is really in terms of a spatial rotation. There it does apply, but it also does apply to cases where this group and its mathematical representation means something different physically.
So basically, I wanted to ask the same thing. So what breaks down when you do boosts? Why can't you do this?
You can play a similar game, I think. Yeah. I mean, but the thing is that the mathematical analysis is already interesting and sort of difficult for SO2. Yeah. So we thought like, yes, we want in the end to talk about boosts and the full Lorentz group, and we want to think about potential particles that may be quantum or not quantum, and ask whether quantum particles are sort of the only possible ones. That would be really fantastic. But the mathematical difficulties are like large. So even here, like understanding what are the spin-1 correlations around a single axis, let's just dive deeply into the mathematics of trigonometric polynomials, harmonic analysis, and orbitopes, right? And then SO3 we could perhaps do as a next step. It just becomes difficult to say, to prove anything rigorous.
For finite dimensional unitary representation.
Yeah, you would have infinite dimensional systems right away, for example, for the Lorentz group. Yeah.
Okay, thank you.
So I wanted to ask that if the Lorentz boost or also the rotation in other reference frames, if we change the do these probabilities remain the same? That the randomness which can be extracted here is the same or not?
Yes, I think I think you shouldn't call our scenario non-relativistic, yeah, because both non-relativistic quantum mechanics and relativistic quantum mechanics in some approximation to quantum field theory does contain the spatial rotations as a subgroup. Yeah. So you can always think of I'm in an inertial frame and I'm just restricting my attention to rotations that don't boost. Right? But certainly when you ask now what about dependence of the probabilities on the boosts or so, right? Then you'd have to need a relativistic treatment and an infinite dimensional representation of the Lorentz group. I'm not sure if that answers your question, but it's sort of where I thought you were heading.
Yeah, it's fine.
Okay.
Sir, one another question is that what is the difference between classical probability and quantum probability?
Yes, I think this would be a question for the whole research field where you say, let's study correlations in certain scenarios, for example, Bell correlations, and let's do that under certain assumptions of our physical theory. For example, you can ask, what are the Alice and Bob two-party Bell correlations for two settings and two outcomes classically, in classical probability theory or in quantum theory or in any kind of non-signaling theory. And you can play a similar game now with others, like with this prepare and measure scenario, for example. So it's certainly, I would say, a well-defined question to ask. To say, suppose I have a theory of a certain type, what sorts of correlations would it predict? This is sort of orthogonal and unrelated to the question of what these probabilities mean. So at least initially it is. So let's say maybe quantum probabilities mean something different from classical ones, right? Because I'm an Everettian and I believe this just so with the branches or whatnot, or your interpretation of probability is theory dependent. The mathematics doesn't care and the classification of the correlations. What you can, however, do in a second step is now to ask, well, the fact that I think quantum probabilities are different has to do with the fact that I can do more with it. I can have protocols that I couldn't do classically. For example, I can have protocols that allow me to securely extract random numbers. Now, this is something you can also show in this sort of reasoning. You ask, here's a scenario, here's what ask what I can do with it. Can I achieve this or that task? And this would say, this characterizes differences between what probabilities can do for you, and then indirectly perhaps what they mean in different physical theories that you might assume.
Okay, that satisfies you? I am asking the student who asked the question. I think he's happy with the answer. So thank you, Marcus. Thank you very much for being online and giving a wonderful talk. Thank you. So this ends the session today. Yeah, thank you very much.
So those who are staying in the guest house, there will be some bus to mini bus to take you to the guest house. For hotel people,